Somewhere, far beyond the glow of our familiar stars, there may be a traveler unlike any other, a beast born from the heart of a galaxy, yet cast away into the endless dark. It drifts alone, untethered, carrying the weight of millions, even billions, of suns crushed into a point so dense that not even light can escape. But unlike the cold, quiet black holes we often imagine hiding in shadow, this one blazes. It burns with a fury brighter than entire galaxies, an unholy beacon that should not exist in the silent depths between the stars. This is not just a black hole, this is a rogue quasar. And if the phrase, hyperactive black hole drifting through space, sends a chill down your spine, it should. But before we continue, subscribe to the channel so you don't miss out on any of these videos. Imagine looking up at the night sky and seeing a point of light so bright that it could rival the moon, and then realizing that this light is not from a friendly star, but from the event horizon of a cosmic monster tearing apart matter with unimaginable violence. Around it, a swirling maelstrom of superheated gas forms a disk spinning at nearly the speed of light. The friction and magnetic chaos in this disk generate torrents of energy, X-rays, gamma rays, and particle streams, powerful enough to sterilize entire solar systems. Now picture that same monster moving, like a predator searching for its next kill. The thought is terrifying because most black holes we know of sit at the center of galaxies, gravitationally anchored like prison inmates serving a sentence for eternity. They don't wander, or at least not far. But a rogue quasar is something else entirely. It is as if the prison gates were blasted open, and the most dangerous inmate was given a weapon of mass destruction, told to roam wherever it pleased. When we think about cosmic threats, our minds often go to asteroid impacts, nearby supernovae, or gamma ray bursts. Those are catastrophic, yes, but they are also quick, moments of destruction. A rogue quasar, on the other hand, is the slow apocalypse. It doesn't just arrive, cause chaos, and fade away. It lingers. It feeds. It corrupts the space around it for millions of years. If the universe were a dark ocean, a rogue quasar would be the glowing maw of some abyssal leviathan, silently gliding toward its prey, unhurried but inevitable. Now imagine the setting. In the vast void between galaxies, an emptiness so complete that the nearest star may be millions of light years away, this blazing monster drifts. No home, no anchor, no allegiance. Its light spreads in all directions, cutting through the black like a wound in reality. The energy it emits is so intense that if you stood anywhere near it, your atoms would be ripped apart in an instant. And yet, from afar, it might seem almost beautiful. That's the cruelty of it. It is a beacon of death masquerading as a jewel of light. Astronomers sometimes compare quasars to lighthouses, but that analogy feels far too gentle. A lighthouse warns sailors away from rocky shores. A rogue quasar doesn't warn, it hunts. It doesn't care whether the ships crash or survive. It only cares about fuel, the next cloud of gas, the next cluster of stars, the next galaxy foolish enough to drift into its path. And in the boundless silence of intergalactic space, it has all the time in the universe to find its meal. If you could watch it from a safe, impossible distance, you'd see jets of energy shooting from its poles, streams of particles moving at nearly the speed of light, cutting across the void for millions of light years. These cosmic lances pierce the darkness like weapons, reshaping everything they touch. If aimed at a planet, these jets could strip away its atmosphere, ignite its surface, or simply render it lifeless in seconds. And unlike most cosmic phenomena, this one moves. It's not confined to a single region, it drifts, gliding past galaxies, sometimes even diving into them, leaving scars in their structure as it feeds and burns. The most chilling thought? A rogue quasar could already be moving toward us right now, its light not yet having reached our eyes. It could be tens of millions of light years away, and we wouldn't know. And even if we did detect it, by the time its light arrives, its true position might be somewhere else entirely, already on a new trajectory, already planning its next kill in the slow, indifferent way only the cosmos can manage. The truth is, in the great hierarchy of universal dangers, rogue quasars sit near the very top. They are not just destructive, they are persistent, relentless, and unstoppable. They don't care about civilizations, about life, about the fragile beauty of worlds. They are ancient, hungry engines of annihilation, wandering the black like ghosts of dead galaxies. And in the infinite lottery of cosmic disasters, you can only hope your ticket is never drawn. A quasar is supposed to be anchored, bound by the gravitational web of its home galaxy so tightly that even the most violent internal events can't loosen its grip. Yet in some rare and extraordinary circumstances, this anchor is broken, and the black hole is set adrift. The idea almost sounds impossible. How could something with a mass of millions or billions of suns, buried deep in the galaxy's core, ever be thrown out? The answer lies in cataclysms so immense that they shake the very fabric of space-time. One of the main culprits is a galactic collision. Galaxies are not static islands. They are in constant motion, drawn to one another by their mutual gravity. When two galaxies merge, their central black holes spiral toward each other in a slow, gravitational dance that can last millions of years. Eventually, they meet. What follows is a cosmic brawl of unimaginable scale, as these titanic objects twist and distort the surrounding space, warping it into waves that ripple outward, gravitational waves. These waves carry away momentum, and in the process, they can give the newly merged black hole an incredible kick. If the kick is strong enough, thousands of kilometers per second, it can hurl the black hole completely out of the galaxy's core, breaking it free from the gravitational bonds of billions of stars. Sometimes, the ejection is even more chaotic. In systems where three supermassive black holes interact, perhaps due to a sequence of rapid galaxy mergers, gravitational slingshot effects can occur. One black hole gets flung away like a stone from a sling, while the remaining two recoil in the opposite direction. In rare cases, that slung-away object is a feeding black hole, still wrapped in its blazing accretion disk. This is when a quasar becomes rogue, suddenly ripped from its throne and sent hurtling into the darkness, carrying its luminous fury with it. Once free, the quasar is no longer bound to orbit anything. It becomes an intergalactic nomad, moving through the void between galaxies at breathtaking speeds. It leaves behind a scar, the host galaxy now stripped of its central powerhouse, its structure subtly wounded. But for the quasar itself, the exile doesn't mean death. If it escapes with enough surrounding gas, or later passes through a region rich in matter, it can continue to feed for millions of years. Without the constraints of a host galaxy's gravitational environment, it can wander anywhere, drifting into smaller galaxies, slicing through gas clouds, even approaching the outskirts of systems that once thought themselves safe from such nightmares. It is this act of violent displacement that makes it rogue. It is no longer tied to the predictable gravitational well of its birthplace. It is a predator without territory, a blazing engine of destruction roaming a universe where almost everything else is tethered to some larger structure. And because these events happen over cosmic timescales, once a quasar is thrown free, it could roam the intergalactic wilderness for longer than life has existed on Earth, carrying with it the scars of its ejection and the hunger that will never be satisfied. At its heart, a quasar is deceptively simple to define, though the reality of what it is feels almost mythic. Imagine a supermassive black hole, a singularity with a mass millions or even billions of times greater than our Sun, sitting in the core of a galaxy. By itself, a black hole is invisible. It does not emit light, it does not glow. But a quasar is what happens when this gravitational monster is actively feeding. As matter, dust, gas, even entire stars, falls toward it, it forms a swirling accretion disk, a flat, rotating maelstrom of material spiraling inward. This disk is no ordinary structure. It is an arena of extreme physics, where matter is compressed and heated to millions of degrees. Friction between the particles, twisted magnetic fields, and the immense gravitational forces combine to generate an outpouring of energy across the electromagnetic spectrum. That energy is so intense that a single quasar can shine brighter than the combined light of all the stars in its host galaxy, in some cases, outshining trillions of suns. From Earth, if you could somehow place a quasar in our night sky at the distance of a nearby galaxy, it would be so bright it could cast shadows. The accretion disk is the engine room, but the quasar's reach extends even further. Near its poles, the chaotic magnetic fields can channel some of the infalling material into colossal jets, beams of matter accelerated to nearly the speed of light and launched far into intergalactic space. These jets can stretch for millions of light years, punching through the gas of the galaxy and continuing into the emptiness beyond. Even without these jets, the light from the disk alone can flood space with X-rays, ultraviolet light, and other forms of radiation deadly to life as we know it. The word quasar comes from quasi-stellar radio source, a name born in the 1960s when astronomers first detected these strange points of light in radio surveys. At first, they looked like stars through a telescope, small and bright, but their spectra told a different story. Their light was shifted toward the red end of the spectrum, a telltale sign they were extremely far away, and therefore unbelievably luminous. The further astronomers looked, the more they realized they were peering back into the early universe, when quasars were far more common. Today, most galaxies' central black holes are dormant, starved of fuel. But when enough matter falls in, the black hole can flare back to life as a quasar, even in the modern era. What makes this so relevant to the idea of a rogue quasar is that the quasar part is a phase, not a permanent state. A black hole can be quiet for billions of years, only to reignite if fresh fuel appears. In its active phase, the light from the accretion disk can travel across billions of light years, meaning we can see quasars from nearly the edge of the observable universe. This extraordinary luminosity is also what makes them dangerous. They are not just massive black holes, but massive black holes with their engines running at full power. When you think of a quasar, picture a whirlpool of fire in space, a cosmic hurricane of matter spiraling into oblivion, surrounded by the blinding halo of its own destruction. It is a paradoxical object, born from darkness but radiating with the brightness of creation. And when such an object is untethered from its home galaxy, it becomes something that no planet, no star system, and no life form would ever want to meet in the dark. The energy output of a quasar is something that almost defies human comprehension. When we talk about powerful cosmic objects, we often speak in terms of stars. A supernova, for example, can release more energy in a few weeks than our Sun will emit in its entire 10 billion year lifetime. That's staggering on its own. But a quasar doesn't burn bright for a few weeks. It can keep this up for millions, even hundreds of millions of years. It is the sustained, relentless brilliance that makes a quasar so terrifying. At its peak, a single quasar can shine with the luminosity of trillions of stars. Think about that for a moment. Every star in our Milky Way, multiplied by tens of thousands, all condensed into the light from one object. This is not the gentle, life-giving glow of a star like our Sun, but an overwhelming flood of radiation across every wavelength, from radio waves to blinding ultraviolet light, all the way up to the most lethal gamma rays. It is a cosmic bonfire so intense that the surrounding space is transformed into a hazard zone, a region where planets, even if they existed, could never hope to survive. The heart of this power lies in the accretion disk. As matter falls toward the event horizon, it is squeezed and heated by friction and tidal forces to temperatures so extreme that electrons are stripped from atoms, creating a plasma that glows with incredible energy. The efficiency of this process is mind-bending. While nuclear fusion in a star converts only about 0.7% of mass into energy, the accretion process in a quasar can convert up to 10%, or even more, of the mass of infalling matter directly into radiation. In astrophysical terms, that is an almost absurd level of efficiency. The result is an energy output that dwarfs anything a normal star could achieve. If you could somehow place a quasar just 30 light-years from Earth, an impossible and instantly fatal scenario, it would dominate our sky, its glare outshining the Sun. Its ultraviolet and X-ray radiation would strip away Earth's atmosphere in short order, boiling the oceans and rendering the surface uninhabitable long before the planet itself was torn apart by tidal forces. And that's just the radiation from the disk itself. Quasars also produce colossal particle jets, streams of matter moving at nearly the speed of light. If one of these jets happened to be aimed in our direction, it would be like standing in the path of a weapon that can fire continuously for millions of years. Even from much greater distances, a quasar's radiation can sterilize entire regions of space. Within a few light years, the intense energy can disrupt the atmospheres of planets, destroy complex molecules, and blast surfaces with so much high-energy light that life has no chance to take root. The most lethal emissions come from the high-energy end of the spectrum, gamma rays and X-rays, which can penetrate deep into planetary atmospheres and even into the bodies of living organisms, breaking apart DNA and triggering mass extinctions. A rogue quasar drifting through space doesn't need to physically collide with a planet to kill it. It can wipe it clean from a distance, leaving nothing but a scorched, airless rock. The scale of this output is also important to understand in terms of cosmic reach. Light from quasars has been detected from over 13 billion light-years away, meaning they were active when the universe was less than a billion years old. The fact that their light can cross such distances and still be visible to us speaks volumes about their power. Now, imagine that same power, not fixed in the center of some distant galaxy, but moving, sweeping through the void like a drifting torch, lighting up and sterilizing any region unlucky enough to cross its path. It's not just a question of brightness, it's the total energy budget. A large quasar can pump out the equivalent of hundreds of times the total energy output of the Milky Way every second. To put that into perspective, if you could somehow harvest all the energy emitted by such a quasar in just 1 second, it would be enough to power human civilization at its current rate for trillions of years. But of course, this energy is not neatly packaged for use. It comes as a deadly, chaotic flood, utterly destructive to anything within range. And unlike more transient cosmic explosions, such as supernovae or gamma-ray bursts, quasars keep going. Their power source is not a single, short-lived event, but a steady diet of gas, dust, and stars. As long as there's something to feed on, the quasar will continue to blaze. In the case of a rogue quasar, drifting between galaxies, that might mean long periods of dormancy punctuated by periods of intense activity whenever it stumbles upon a new supply of matter. During those active phases, the energy it releases can alter the structure of entire galaxies, heating and pushing away the gas that might otherwise have formed new stars. If such an object were to drift close to our galaxy, it would not need to come anywhere near Earth to threaten us. A rogue quasar lighting up within even tens of thousands of light-years could still flood vast swaths of the Milky Way with enough radiation to disrupt planetary systems and potentially trigger extinction events. The fact that these objects can operate on such scales, affecting not just individual worlds but entire star systems and galactic regions, is why they are among the most dangerous phenomena the universe can produce. There is a certain poetry in this danger, a beauty that hides its lethality. Through our telescopes, quasars appear as small points of light, like distant stars. But what we are really seeing is a maelstrom of annihilation, an unrelenting storm of energy powered by a singularity devouring everything in its reach. For a rogue quasar, there is no boundary, no home, and no rest, only the infinite darkness, and the next meal that will keep the fires burning. The ejection of a supermassive black hole, and in rare cases, a blazing quasar, from the center of its galaxy is one of the most extreme acts of violence the cosmos can perform. Under normal conditions, the gravitational pull of billions of stars, vast clouds of dark matter, and the sheer mass of the galaxy itself keep its central black hole firmly locked in place. Dislodging such a titan requires a truly catastrophic event, something so powerful that it can overcome the deep gravitational well at the galaxy's heart and fling the black hole out into the cosmic wilderness. One of the most dramatic ejection mechanisms is the collision of galaxies. Across the universe, galaxies are constantly drawn together by gravity, and when they meet, the result is a slow-motion cataclysm. Stars pass each other largely unharmed because the space between them is vast, but their central black holes are another story entirely. As the galaxies merge, their supermassive black holes begin to spiral inward toward one another in a gravitational waltz. They shed momentum by disturbing the surrounding stars and gas, and, as they draw closer, they enter the realm of gravitational wave emission, ripples in the very fabric of space-time. When the two black holes finally merge, the gravitational waves they emit are not perfectly symmetrical. If the waves carry away more momentum in one direction, the merged black hole will recoil in the opposite direction, a phenomenon known as a gravitational wave kick. The strength of this kick depends on the masses of the black holes, the speed of their spins, and the directions of those spins relative to each other. In some extreme configurations, the recoil velocity can reach several thousand kilometers per second. That's fast enough to escape the gravitational pull of an entire galaxy. In other words, the newly merged black hole, possibly still wrapped in its blazing accretion disk, is hurled into intergalactic space, condemned to roam forever. But gravitational wave kicks aren't the only way a quasar can be ejected. In cases where three supermassive black holes end up in the same galactic nucleus, often the result of multiple mergers occurring over relatively short cosmic timescales, a gravitational slingshot effect can occur. The interaction between three massive bodies is inherently unstable, and often the lightest of the trio is violently ejected while the other two remain bound. In the process, the expelled black hole can be accelerated to incredible speeds, tearing it away from its galaxy entirely. If this black hole happens to be in an active feeding phase, it will carry its quasar-like brilliance with it into the dark. Another possible mechanism involves tidal stripping during a galaxy encounter. If a smaller galaxy hosting a quasar passes too close to a much larger galaxy, the gravitational forces can shred the smaller galaxy apart, pulling away its stars and gas. In some cases, even the central black hole can be yanked out, left drifting in space with only a fraction of its former surroundings. While it may dim if it loses its fuel source, a quasar in such a state can reignite later if it finds new matter to consume. What makes these ejection events so terrifying is the combination of their rarity and their persistence. They are rare enough that most galaxies will never experience them, but once a quasar is set loose, it becomes a threat to any region of space it passes through for potentially hundreds of millions of years. Unlike a supernova or gamma-ray burst, which are devastating but fleeting, a rogue quasar is an enduring hazard. It can travel vast distances, cross the void between galaxies, and flare into activity again and again whenever it encounters fresh material to feed upon. From a cosmic perspective, these mechanisms are like the universe's way of loading a weapon and then letting it drift, safety off, across the cosmos. The collision of galaxies, the merging of black holes, the chaotic dance of multiple supermassive monsters, all are capable of creating one of the most dangerous objects in existence, then sending it on a journey without destination or purpose. It is a chilling reminder that the forces shaping the universe are not only creative but also destructive, and that the most brilliant lights in the night sky can sometimes be the most lethal. When two supermassive black holes collide, the event is anything but quiet. It is a cosmic detonation in the medium of space-time itself. As they spiral inward during the final stages of their merger, their enormous masses create ripples that race outward at the speed of light, gravitational waves. These waves don't carry matter the way light carries photons, but they do carry energy and momentum. And that momentum can be uneven. If more gravitational wave energy is emitted in one direction than another, the newly merged black hole will be shoved in the opposite direction, like a massive cannon recoiling after firing a shell. This is the gravitational wave kick. The scale of this recoil is staggering. Most black holes don't get much of a push at all, perhaps a few hundred kilometers per second, not enough to escape their galaxy. But in rare, extreme circumstances, the alignment of the two black holes' spins and their relative masses can combine to produce a truly enormous kick. If the spins are misaligned and oriented just right, the asymmetry in gravitational wave emission can hurl the merged black hole away at speeds exceeding 5,000 kilometers per second. That's fast enough to leave even the deepest gravitational wells of massive galaxies behind, turning what was once a galactic anchor into a free-floating wanderer in the dark. Now imagine that this black hole was not dormant, but actively feeding at the time of the merger. It would still be surrounded by its accretion disk and possibly even its relativistic jets. Those structures are tightly bound by gravity to the black hole itself, so they'd come along for the ride. The result would be a quasar launched like a bullet from the heart of its galaxy, carrying with it the blazing energy output of a trillion suns. In the moments after the kick, it would rip through the dense central regions of the galaxy, scattering gas and stars in its wake, before bursting free into the thin halo and finally into the vast intergalactic void. The physics behind this is a fascinating and violent dance. As the two black holes spiral closer, each one drags the fabric of spacetime into a whirlpool around it. If their spins are uneven, the warping of spacetime isn't balanced. In the instant they merge, the shape of space itself changes violently, and the imbalance in wave emission is like a cosmic shove. The recoil is not gradual. It happens in a single, intense moment, a fraction of a second where the new black hole's velocity changes abruptly. For an object with millions or billions of times the mass of the Sun, to be accelerated so suddenly is almost incomprehensible. Once the gravitational wave kick has done its work, there's no pulling the quasar back. Galaxies don't have a way to catch something moving that fast. It becomes a projectile on an endless journey, and because black holes don't slow down by much in the emptiness between galaxies, it will keep traveling for billions of years. Along the way, it may pass through other galaxies or gas-rich regions, reigniting its quasar activity each time it finds fresh material to consume. The detection of these kicks is indirect but compelling. Astronomers have found quasars whose bright cores are slightly offset from the center of their host galaxies, or whose light appears to be moving relative to the surrounding galaxy. These could be snapshots of quasars caught mid-flight, still carrying their momentum from a past gravitational wave kick. The idea that we could be observing a quasar in the act of escaping its galaxy is both scientifically thrilling and deeply unsettling. It means that the universe is not just capable of producing these wandering monsters, but that it is doing so even now. A rogue quasar, set adrift in the silent ocean of intergalactic space, carries with it all the hunger of a cosmic predator. Unlike a quasar tethered to the bustling core of its birth galaxy, this one roams freely, no longer bound by the familiar boundaries of home. Its trajectory could carry it into regions dense with interstellar gas, dust, and even unsuspecting star systems, resources it can devour to fuel its brilliant, destructive appetite. There's no need for it to announce its approach. From light years away, there is no ominous glow marking its path in advance. The light of its feeding frenzy flares only when matter gets too close, spiraling inward. In the stillness of space, a rogue quasar can behave like a silent shark gliding through an endless cosmic reef. It does not require the chaos of a galaxy core to thrive, it simply needs material to consume. A drifting cloud of hydrogen in the path of its gravity can be pulled in, compressed, and heated until it glows with searing intensity, joining the maelstrom of its accretion disk. A lone star, unlucky enough to wander near, can be torn apart in a violent tidal disruption event, its mass shredded into streams of plasma that spiral inward, igniting bursts of radiation so intense they could sterilize any nearby planets in moments. The danger lies not only in its ability to feed but in its persistence. Without the limits imposed by its host galaxy's gravitational neighborhood, a rogue quasar can cover immense distances over millions of years, drifting from one potential feeding ground to the next. In its wake, it leaves nothing but empty space and faint trails of high-energy particles. Any life that might have existed on planets orbiting stars it consumes would vanish without warning, erased in seconds by an invisible approach that gives no time for escape. Even when it's far from anything substantial to devour, a rogue quasar remains dangerous. Its gravity subtly disrupts the paths of stars and planetary systems it passes near, sometimes destabilizing orbits and triggering collisions. And should it enter a dense star cluster, the feast could become almost immediate, a cascade of destruction as one star after another is stripped, shredded, and swallowed, with each death fueling its light to even greater brightness. In the darkest corners of space, these objects blur the line between an astronomical phenomenon and a predator in the truest sense. They are relentless, guided only by the physics of gravity and momentum, indifferent to what worlds or civilizations they race. And because they are moving, unpredictably and invisibly, there's no telling where the next one might be, or if it's already on a slow, inevitable path toward us. The true menace of a rogue quasar is unleashed in the form of its radiation. As matter spirals into the event horizon, it is compressed, shredded, and superheated to temperatures that defy comprehension. The surrounding accretion disk becomes an inferno, glowing not just with ordinary light but with a spectrum that stretches far into the dangerous high-energy range. Gamma rays pour out in immense quantities, each photon carrying enough energy to disrupt the molecular bonds that sustain life. X-rays emerge in floods capable of stripping electrons from atoms across vast stretches of space. This is not gentle starlight, it is the cosmic equivalent of a blowtorch, invisible to the human eye but lethal to anything biological. From the poles of the quasar, the danger becomes even more focused. The magnetic fields generated by the swirling plasma near the black hole act like twisted rails, guiding particles into tightly collimated jets. These jets are made of matter accelerated to nearly the speed of light, protons, electrons, and other subatomic fragments transformed into an unstoppable beam. They stretch for thousands, sometimes even millions, of light years, piercing the intergalactic darkness like cosmic spears. If a planet or star system lies within the path of one of these jets, the outcome is catastrophic. Atmospheres can be stripped away, surfaces sterilized, and the delicate chemistry needed for life obliterated in an instant. What makes these particle jets and radiation fields so insidious is their reach. Light from a quasar can be seen across the universe, which means its high-energy emissions can travel just as far. In interstellar space, there is no protective atmosphere, no magnetic field, no thick layer of gas to absorb the onslaught. Any unlucky system in range is exposed directly to the quasar's fury. Even at a distance of hundreds or thousands of light years, the intensity could be enough to trigger mass extinctions on a habitable world, much like the effects of a nearby gamma-ray burst but sustained for millions of years instead of mere seconds. In the case of a rogue quasar, the danger is compounded by its mobility. A quasar anchored in the heart of a galaxy is terrifying, but at least its position is fixed, making its destructive cone of radiation relatively predictable. A rogue quasar, however, drifts. It can move into entirely new regions of space, carrying its jets and radiation field into areas where stars and planets have existed in peace for billions of years. For civilizations unaware of its approach, the danger might only become apparent when the night sky begins to change, when an unusually bright star appears and grows steadily more luminous. By the time they realize it's a quasar closing in, it could already be too late to escape the reach of its deadly beams. The particle jets themselves are phenomena of extraordinary violence. Their creation begins deep in the quasar's accretion disk, where matter whirls around at relativistic speeds, compressed into an impossibly hot plasma. The black hole's intense spin drags spacetime around with it, a process known as frame dragging, and the powerful magnetic fields in the disk twist into tight spirals. These spirals channel particles along the quasar's rotational axis and hurl them outward at speeds just shy of the speed of light. At these velocities, the kinetic energy of each particle is immense. Even a single proton could deliver the punch of a small-scale explosion if it collided with matter. Now multiply that by countless trillions of particles pouring out every second, and you begin to grasp the scope of the danger. But the lethal radiation doesn't stop with gamma rays, X-rays, and particle beams. Quasars also bathe their surroundings in intense ultraviolet radiation, which is more than enough to break apart organic molecules and strip atmospheres of protective ozone layers. For a planet caught in this ultraviolet storm, even if it survives the immediate blast of gamma and X-rays, the long-term effects would be equally fatal. The atmosphere would erode, the surface would be exposed to unfiltered starlight, and any remaining liquid water would evaporate into space. What's left would be a dry, lifeless husk, a silent monument to the quasar's passing. The scale of destruction is also tied to the quasar's ability to operate on timescales that dwarf human history. While a gamma-ray burst lasts for seconds or minutes, a quasar can remain active for tens of millions of years. That means the radiation hazard isn't a brief cosmic event, it's a sustained siege. If a rogue quasar wandered into the outskirts of a galaxy and aimed its jets toward a populated star system, the inhabitants would not have to survive a single wave of destruction. They would have to endure continuous bombardment for epochs, watching as their planet's atmosphere and oceans vanished, their biosphere burned away by relentless high-energy light. Even systems outside the direct path of the jets wouldn't be entirely safe. The diffuse radiation leaking from the accretion disk is still more than enough to cause devastation. This background glow of high-energy photons would gradually poison any exposed biosphere, altering DNA, driving up mutation rates, and potentially triggering collapse in complex ecosystems. Over centuries, the effects would accumulate, erasing the fine balance that life depends on. In intergalactic space, where a rogue quasar might travel after being ejected from its home galaxy, the hazard takes on a different form. Here, the quasar would drift through regions largely devoid of stars, but when it crosses paths with a cloud of interstellar gas, the feeding frenzy begins anew. The accretion disk flares brighter, the jets sharpen and intensify, and the reach of its lethal emissions extends farther still. Any isolated stars or planetary systems in the region could suddenly find themselves in the kill zone without warning, victims of a predator they could never have anticipated. The combination of stealth, range, and sheer destructive output is what makes a rogue quasar's radiation hazard unmatched in the universe. It doesn't need to collide with a planet to kill it. It doesn't need to come within a few light years to leave a mark. Its weapons are beams of light and matter traveling at relativistic speeds, cutting through the void with surgical precision. And unlike most dangers in the cosmos, these weapons are not silent and invisible. They blaze with such ferocity that the quasar itself becomes a beacon, announcing its presence to the universe. But that light is not an invitation. It's a warning. A signal that somewhere out there, a monster is awake, feeding, and bathing the cosmos in lethal fire. The death zone around a rogue quasar is not something that any planet, star system, or even interstellar cloud would want to find itself inside. It's a volume of space so saturated with destructive energy that life, technology, and even the chemical bonds holding matter together can be obliterated. Unlike the blast radius of an explosion, which dissipates quickly, the danger from a quasar is sustained for millions of years. Its engines never rest. The supermassive black hole keeps pulling in matter, and as it does, the magnetic fields in its accretion disk twist and snap like cosmic whips, flinging out radiation and particles in two focused jets from its poles. These jets aren't just beams of light. They're concentrated torrents of energy, accelerated to nearly the speed of light, punching straight through anything in their path. The scale of destruction is difficult to overstate. For life as we know it, even a fraction of this energy is lethal. High-energy gamma rays rip through atmospheres, breaking apart molecules, shattering DNA, and stripping away protective ozone layers. For a planet unlucky enough to be in direct line with a quasar jet, the entire biosphere could be wiped out in a geological blink. Oceans would evaporate, air would be ionized, and any surviving molecules on the surface would be bombarded into chemical oblivion. Even worlds with thick atmospheres and strong magnetic fields wouldn't stand a chance. The onslaught of energy is simply too great, bypassing most planetary defenses. The real horror is that this death zone isn't limited to a single solar system. A quasar's particle jets can stretch for hundreds of thousands, even millions, of light years. Their brightness is so intense that they can be seen across the universe, which means their reach is unfathomably vast. And while their energy disperses with distance, the most powerful quasars still emit enough radiation to sterilize planets from light years away. The death zone could encompass entire star clusters, turning rich, life-filled regions into barren wastelands. In fact, astronomers speculate that quasars in the early universe may have been one reason why life took so long to gain a foothold. Their lethal glare could have repeatedly reset the clock on any emerging ecosystems. What makes the death zone of a rogue quasar especially terrifying is its mobility. A stationary quasar anchored in the heart of a distant galaxy is bad enough, but a rogue one, drifting through intergalactic space, can wander into entirely new regions. It's like a mobile cosmic doomsday machine. Entirely unsuspecting systems could find themselves in its crosshairs without warning, especially if they lie along the path of its polar jets. And because quasars are so bright, the visible light they emit could be the only early warning, but by the time that light reaches you, the radiation and particle storms are already well on their way. The lethality is not just about instant destruction. There are more insidious consequences as well. If a planet is in the outer range of the death zone, it might not be vaporized outright, but its climate and habitability could be ruined. High-energy radiation could alter atmospheric chemistry, creating toxic compounds and blocking essential sunlight. Cosmic rays could increase mutation rates so drastically that complex life collapses under the weight of genetic damage. Civilizations reliant on electronics and satellites would be devastated as radiation fried circuits, disrupted communications, and destroyed power infrastructure. In this way, a rogue quasar doesn't just kill, it can cripple, destabilize, and erode the conditions for life over long spans of time. The energy output is staggering to consider. A single quasar can outshine an entire galaxy containing hundreds of billions of stars, and all of that power is being generated in a region no larger than our solar system. Imagine compressing the light and heat of billions of suns into a single, unstoppable beacon, then aiming it like a sniper rifle across the cosmos. This is why the term, death zone, is not hyperbolic. The destructive range is measured not in planetary diameters but in parsecs, in light years, in volumes of space large enough to engulf civilizations we might never even know existed. And here's the cruel irony. A rogue quasar might be invisible to us until it's far too late. While their visible light is bright from a distance, if a quasar approaches from an angle where its jets aren't pointing toward us, we might underestimate its danger. Yet all it takes is a shift in the feeding black hole's spin or a tilt in the accretion disk to redirect those jets, instantly placing us within the lethal zone. In cosmic terms, this could happen over a mere few thousand years, which is the blink of an eye on galactic timescales. The stars and planets in its path wouldn't even know they'd been marked for destruction until the radiation began to hit. For wandering quasars, there is no negotiation, no escape, no mercy. They are forces of nature operating on scales we can barely comprehend, indifferent to whatever life or worlds lie ahead. Their death zones are not personal weapons. They are simply the inevitable consequence of the laws of physics when matter is consumed at such ferocious rates. And somewhere out there, far from the safety of their home galaxies, rogue quasars drift silently, carrying their invisible spheres of annihilation across the deep. They are the ultimate reminder that in space, danger is not always about proximity. Sometimes, the most lethal threats can find you across the emptiest distances imaginable. If a rogue quasar were to drift close enough to a planetary system, the devastation would not come with the slow inevitability of orbital shifts or gradual stellar dimming, but rather with the ferocity of an entire cosmos bearing down at once. The moment the system came within range of the quasar's energetic output, the delicate balance that allowed planets to harbor stable atmospheres, liquid water, and complex chemistry would begin to unravel. Gamma rays, invisible but unimaginably energetic, would slice through the upper layers of planetary atmospheres, breaking apart molecules, stripping away protective ozone layers, and bombarding the surface with sterilizing radiation. X-rays, equally insidious, would penetrate deep into the atmosphere, generating cascades of charged particles that could fry electronics, mutate DNA, and destabilize chemical bonds essential for life. Even worlds protected by thick atmospheres or buried oceans would not remain safe for long. The radiation would seep into every crevice, heating and destabilizing environments in ways that would make survival almost impossible. The most immediate effect would be atmospheric erosion. As the quasar's radiation collides with atmospheric particles, it injects tremendous energy into them, causing gases to heat and expand. In the absence of strong magnetic shielding or deep gravity wells, this heated atmosphere could escape into space, carried off in a wind of ionized particles. Over time, or in this case, frighteningly quickly, planets could be stripped down to barren, airless rocks, unable to support life in any form. Even gas giants, with their enormous atmospheres, could not escape unscathed. Their upper layers could be blasted away, their magnetic fields warped, and their moons sterilized. But it wouldn't just be the radiation working its slow, unrelenting magic. Rogue quasars often unleash enormous jets of matter, streams of electrons and protons accelerated to nearly the speed of light. If one of these relativistic jets were aimed even loosely toward a planetary system, the energy flux would be catastrophic. These jets carry momentum and energy capable of reshaping magnetic fields and delivering bursts of radiation many orders of magnitude stronger than the background of normal cosmic rays. Even a brief encounter could deposit enough energy into a planet's atmosphere to trigger chemical reactions on a global scale, perhaps turning nitrogen and oxygen into toxic nitrogen oxides, or vaporizing vast amounts of surface water. The effect on the star itself would be subtler but no less destructive. Stars are robust compared to planets, yet they too exist in a gravitational and energetic balance that can be disturbed. The intense radiation from the quasar could heat the outer layers of a star unevenly, potentially disturbing its magnetic field cycles or even accelerating mass loss. For smaller stars, this could shorten their lifespans. For more massive stars, it could trigger unpredictable bursts of solar activity. In either case, the combined radiation from both the local star and the quasar would raise the environmental danger in the surrounding system to unimaginable levels. If life had developed on any planet in that system, its fate would be sealed almost instantly once the quasar approached close enough. The most radiation-hardy microbes might hold out for a while, sheltered deep underground or beneath thick ice, but the relentless bombardment of energy would eventually break even the toughest molecular structures. Complex, multicellular organisms, with their delicate DNA, proteins, and cellular machinery, would have no chance. Evolutionary adaptation works on timescales far longer than the onslaught of a quasar's approach. Survival would require defenses more suited to a science fiction civilization than to biology, as we know it. And even if some worlds survived the radiation directly, the gravitational influence of the quasar could still wreak havoc. A supermassive black hole, even if it is merely passing by, exerts a gravitational pull that could destabilize planetary orbits. The outer planets might be tugged into elongated, unstable trajectories, slingshotting comets and asteroids inward toward the inner planets. This could trigger a secondary wave of destruction, meteor impacts, gravitational collapses of planetary rings, or even planetary ejections entirely out of their solar system. The quasar wouldn't even have to come particularly close for this. Given its mass, its sphere of influence could stretch across light years. If the planetary system's star were particularly unlucky, the quasar could strip it of its gas and dust reservoir, robbing it of the materials needed to form new planets or replenish asteroid belts. In extreme cases, the quasar might capture material directly from the star, siphoning it into its own accretion disk and feeding its already insatiable hunger. Imagine a star slowly being consumed from afar, its outer layers drawn out into a vast, glowing spiral that stretches toward the quasar's central maw. From the perspective of any intelligent civilization in such a system, the first warning signs might be subtle: an increase in high-energy radiation levels, a strange dimming or flickering of the sky in one direction, a rise in mutation rates in crops and wildlife. But the escalation would be swift. Once the quasar's jets and radiation fields fully engulf the system, there would be no realistic path to survival without abandoning the homeworld entirely. Space-faring civilizations might attempt desperate evacuations, fleeing to distant systems. But even interstellar travel would be risky if the quasar's influence spanned a large swath of local space. Perhaps the most unsettling thought is that the damage doesn't require a direct hit. A rogue quasar passing even a few dozen light-years away could still bathe a planetary system in enough radiation to cause mass extinctions. Earth itself, for example, could be sterilized from such a distance if a particularly energetic quasar were to align its jet toward us. In this way, rogue quasars act as silent executioners in the universe. They don't need to collide or even approach closely to erase entire worlds from existence. The destructive potential of a rogue quasar passing near a planetary system is a reminder that, in the cosmic scale of danger, proximity isn't the only factor. It's about energy, scale, and alignment, and a quasar has all three in abundance. Even in the vast emptiness of intergalactic space, where one might imagine safety in isolation, the wrong kind of visitor can turn a thriving planetary system into a lifeless monument to the power of the cosmos in a matter of moments. Drifting between galaxies, a rogue quasar moves through the vast, almost incomprehensible voids of intergalactic space like a phantom on a ceaseless journey. There is nothing that can tether it, no gravity well strong enough to recapture it once it has been flung from the embrace of its home galaxy. It is the ultimate cosmic exile, yet also the ultimate wanderer, a predator without territory, gliding through the darkness in search of the next source of fuel to awaken its hunger again. These intergalactic nomads are not bound to the slow, predictable orbits of stars within a galactic disk. Instead, they follow trajectories determined by the colossal events that ejected them, trajectories that can cut across the silent void for millions, even billions, of light years. Out here, in the deep reaches where galaxies are little more than dim smudges in the black, a rogue quasar shines as an impossibly bright beacon. Its light and radiation can be detected across almost the entire observable universe, even if it's millions of parsecs from the nearest spiral or elliptical galaxy. From a distance, this might appear beautiful, a single point of blazing light in an otherwise empty canvas. But up close, it is an engine of chaos and annihilation, a self-sustaining furnace capable of stripping life from worlds long before they ever even glimpse its true form. Their paths between galaxies are unlike anything in the more crowded cosmic neighborhoods. Most stars live and die without ever venturing far from their birthplace, their movement governed by the balance of their galaxy's mass. But a rogue quasar is different. The forces that launch one are so extreme that its velocity can exceed thousands of kilometers per second. With that speed, the gravitational pull of its galaxy becomes meaningless. It will not slow, it will not turn back, and it will not be drawn into orbit around another unless it passes dangerously close. Even then, its fate depends on delicate gravitational interactions. Often, it will simply slingshot past any new galaxy, continuing on its eternal voyage. In these immense gulfs, the rogue quasar may pass through regions so empty that it encounters almost no gas for millions of years. During such times, it may appear dormant, its once blazing accretion disk dimming as the supply of matter runs dry. The radiation jets narrow, the energetic winds weaken, and the quasar becomes less visible to the universe's watchful eyes. But dormancy does not mean death. All it takes is one encounter with a pocket of gas, a stray molecular cloud, or the outskirts of a small dwarf galaxy, and the beast awakens again. Matter spirals in, friction and gravity crush it into unimaginable heat, and the darkness around it explodes with light and energy. In an instant, it transforms from a quiet traveler into a force that can be seen from across the cosmos. What makes them truly unstoppable is that there is no mechanism to slow them on cosmic timescales. Friction does not exist in space in the same way it does on Earth. There's no air resistance to rob it of momentum, no thick medium to sap its speed. Even the tenuous gas and dust that drift between galaxies barely register against its colossal inertia. Over billions of years, this means it will keep going indefinitely, crossing from one galaxy cluster to the next, perhaps even moving beyond the great cosmic web into regions of the universe so empty that light itself struggles to find a path. From a human perspective, their movement is glacial. Thousands of kilometers per second might sound fast, but when the distances are measured in millions of light years, even that speed stretches the journey into spans longer than the entire history of our planet. And yet, in the universe's own timescale, they are swift, their journeys allowing them to cross the space between galaxies within the lifetime of the cosmos. Some may have been set in motion not long after the first galaxies formed, flung out by chaotic mergers in the universe's youth, and are still traveling today, carrying with them the echoes of that ancient violence. Astronomers suspect that some of the most distant quasars we detect could already be in this nomadic state, isolated in intergalactic space, their light only now reaching us after billions of years. The thought is unsettling. They may have passed close to other galaxies long before ours even existed, sterilizing planets, or triggering vast cosmic changes before moving on without ever slowing down. And one day, a rogue quasar on such a path could pass near our own galaxy. The chances are vanishingly small, but small, in cosmic terms, is still not zero. And the universe has an endless patience for improbable events. In many ways, these intergalactic wanderers are like cosmic sharks, never stopping, always moving, sustained by the rare but devastating meals they find along their path. Their existence is a reminder of the violence and unpredictability of the universe, that not all threats come from within our own stellar neighborhood. Some arrive from beyond, ancient travelers whose journeys began with cataclysms so immense that the shockwaves of their origin can still be felt in the structure of galaxies today. And they will keep drifting, unstoppable, until the universe itself grows cold and dark, their light fading into the silence of a cosmos long past its prime. speed becomes one of the most unsettling factors when considering rogue quasars. In the mind's eye, it's easy to imagine them as slow drifters in the cosmic dark, creeping along at a pace that would take eons to cross even the smallest interstellar gaps. But reality is far less comforting. When a quasar is ejected from its home galaxy, often by the catastrophic recoil from a supermassive black hole merger, it can be hurled away at astonishing velocities. We're not talking about a few hundred kilometers per second, which is already mind-boggling in human terms. These objects can be propelled at speeds of thousands of kilometers per second, fast enough to cross the distance from Earth to the Moon in just a few minutes. At such speeds, the concept of slowly drifting doesn't apply. They're on a relentless, straight-line trajectory through space, cutting across the intergalactic void like a cosmic bullet. This speed isn't just a number, it's a problem for anything in their path. Even though space is unimaginably vast and the chances of a rogue quasar directly intersecting with a populated system are statistically small, its velocity makes avoidance nearly impossible. A planetary system wouldn't have decades or centuries of warning to prepare. Depending on the distance, the quasar could emerge from the darkness and begin affecting its surroundings within a geological blink of an eye. That speed also means the quasar carries enormous kinetic energy in addition to the terrifying radiation it spews. While it's not a physical projectile in the traditional sense, its gravitational influence sweeps through space like a moving well of doom, capable of destabilizing orbits and drawing in unlucky material to feed its accretion disk. The speed of a rogue quasar also plays into its survival in the vast, hostile emptiness between galaxies. A slower object might eventually run out of nearby material to consume, fading into dormancy as its accretion disk cools and dims. But a fast-moving quasar constantly encounters new sources of gas, dust, and even rogue stars in intergalactic space. Its hunger never truly stops. Over millions of years, it can cross from one galaxy cluster to another, perhaps even weaving through multiple galaxies in its lifespan, reigniting its brilliance each time it finds fresh fuel. In this way, its velocity ensures its longevity, turning it into an eternal wanderer and threat. Another consequence of this high velocity is that it renders the quasar effectively untouchable by galactic structures. Gravity, even on a galactic scale, struggles to capture something moving at thousands of kilometers per second. While ordinary rogue stars can sometimes be recaptured or slowed by a galaxy's pull, rogue quasars are simply too fast. They slip through halos of dark matter and streams of intergalactic gas without being trapped. This freedom from gravitational imprisonment means they don't follow predictable paths, no closed loops around the galactic core, no return home. Once ejected, their journey is one way, heading deeper into the black at speeds that defy any hope of containment. From a human perspective, the speed of a rogue quasar is both abstract and deeply horrifying. We measure our fastest spacecraft in tens of kilometers per second. Quasars can move hundreds of times faster than that. If one were traveling toward our region of space, the distances might make it seem safe, but the timeline would be deceptive. Even from millions of light years away, the timescale of approach would still be short compared to cosmic history. It's possible that somewhere, far out in the darkness, such a quasar is already making its way toward the Milky Way, its approach masked by distance and the fact that we can't detect every object lurking between the galaxies. Given the speeds involved, by the time we noticed it, there might be no real way to alter the outcome. In the grand scheme of cosmic motion, rogue quasars are like intergalactic predators on a relentless migration. Speed is their stealth. They cross unimaginable gulfs before we even know they exist. In the vast timeline of the universe, their journeys are not slow meanders but swift, decisive incursions. And while most will remain far from our little corner of the cosmos, the knowledge that such fast-moving engines of destruction roam untethered adds yet another layer of unease to our understanding of the universe. They are not bound by the rules of ordinary stars or galaxies. They have no fixed home, no predictable orbit, and no reason to ever stop. Once set in motion, they are pure momentum and pure menace, streaking across the dark like cosmic hunters that will never tire. Across the incomprehensible stretches of the universe, rogue quasars carry with them a paradox of cosmic detection. They are among the brightest and most energetic objects ever known, yet their danger lies in the fact that, depending on their distance and direction, they can remain completely hidden from our awareness until it is already too late to act. Light, as fast as it is not instantaneous. When we look into the night sky, we are always looking back in time. If a quasar is several billion light-years away, the light reaching our eyes tonight actually began its journey before Earth had even formed. The same is true for rogue quasars, and that delay works entirely in their favor when it comes to hiding their approach. The light from such an object could take millions, or billions, of years to get here, meaning that by the time we see its glow in our telescopes, the rogue quasar might already have moved, possibly much closer than we think. We might be staring at an image of its past, unaware of its true current location. Compounding the threat is the fact that rogue quasars are often found far from the dense, star-filled regions where astronomers spend most of their observing time. They can roam through vast intergalactic voids, those dark stretches between galaxies where few instruments are trained. A quasar inside a galaxy is easier to detect because its radiation interacts with surrounding matter, making it obvious in surveys. But a rogue quasar drifting through nothingness, away from gas clouds or star fields, might appear faint, or even invisible until it crosses into an area dense enough for its accretion disk to flare back to life. In other words, it could spend millions of years traveling under our radar, only to suddenly become a brilliant, and deadly, beacon when it finds something new to devour. The energy output of a quasar isn't uniform in all directions. Much of its deadliest radiation, including its powerful particle jets, is focused along its rotational axis, narrow beams that can span hundreds of thousands of light-years. This directional nature makes detection tricky. If a rogue quasar's jets are not pointed even loosely toward us, its radiation signature could be dramatically reduced from our perspective, blending into background noise. We might catalog it as an unremarkable radio source or a dim infrared object, never realizing it is in fact a supermassive black hole hurtling through space at unimaginable speeds. Conversely, if the beams are aimed our way, we may detect it easily, but that would also mean we're directly in the path of its most hazardous emissions. Even our best sky surveys are not immune to blind spots. Telescopes are limited by atmospheric interference, seasonal sky coverage, and even the sheer size of the universe. Many rogue quasars may simply be positioned in areas we haven't scanned deeply enough. And the issue is made worse by the nature of cosmic travel. By the time our data flags a suspicious, high-energy source, it could already be tens of thousands of light-years closer than its last recorded position. On a galactic timescale, that's a blink of an eye. Imagine detecting one today at a comfortable distance, only to realize in a future survey that it has closed the gap significantly, without any warning in between. Adding another layer of uncertainty is the concept of redshift, the stretching of light waves as they travel through the expanding universe. The more distant an object is, the more its light is shifted toward the red end of the spectrum. While this allows us to estimate distance, it also means that the true energy profile of a rogue quasar might be disguised by its apparent color and brightness. A quasar with a moderate redshift could appear to be much farther and safer than it actually is if its velocity relative to us is unusual. High-speed motion toward our position could counteract some of the redshift and distort the signals we rely on, further clouding the picture of where it is and how fast it's approaching. The terrifying implication is that a rogue quasar could be much closer than our instruments suggest, moving on a trajectory that will bring it near, or even through, our galaxy in a time frame that is astronomically short. Astronomers rely on years, even decades, of observations to track such objects and predict their movements. But for a rogue quasar ejected from a galaxy billions of years ago, we may be catching only the faintest glimpse of its ancient history, not its current, potentially perilous position. It's like seeing the muzzle flash of a gun long after the bullet has already been fired, and not knowing where the bullet is now. When its light finally arrives in sufficient strength to catch our attention, the event we are witnessing has already happened ages ago. If it's on an inbound course, there's no way to slow or divert it, and the damage from its radiation could be inevitable. In such a case, the warning we receive might be purely academic, a grim reminder of the timescales we are forced to work with in cosmic observation. The quasar's true arrival, or the moment when its radiation begins to meaningfully affect our local space, might already be in motion, its effects inevitable long before we understand the scope of the threat. The universe gives us no convenient system of alerts, no early warning beacon for intergalactic hazards like these. It is a vast and indifferent stage where the actors perform their deadly roles in silence, their light delayed, their motions masked by distances so great that even light, the fastest thing in existence, becomes a sluggish courier. Rogue quasars thrive in that delay, wandering undetected until the moment their brilliance bursts into view, by which time the play's ending might already have been written in the stars. Although rogue quasars are among the rarest phenomena in the cosmos, the scientific evidence for their existence is far from speculative. Their rarity stems from the fact that the conditions required to create them are both extreme and infrequent. It's not every day, even on a cosmic timescale, that a supermassive black hole is both active and violently expelled from its galactic cradle. But modern astronomy has armed us with the tools to detect these rare beasts, and over the past few decades, certain observations have strongly hinted, and in some cases outright confirmed, that such objects are real. The story of how scientists know they exist is almost as fascinating as the quasars themselves. It begins with a simple truth about light. Even though it travels at an incredible speed, it takes time to reach us from distant corners of the universe. When we peer into deep space, we are also peering back in time, sometimes billions of years into the past. This means that even though rogue quasars may be hurtling through intergalactic space right now, what we see is their light from eons ago, captured by sensitive telescopes that act like time machines. Detecting a rogue quasar isn't as simple as spotting a bright dot in the sky, because quasars are already incredibly luminous and can look similar whether they're inside a galaxy or not. Instead, astronomers rely on patterns, subtle clues that betray their isolation. One of the most compelling pieces of evidence comes from quasars that appear suspiciously displaced from the centers of galaxies. Normally, an active quasar sits snug at the heart of its galaxy, surrounded by swirling stars, dust, and the telltale spiral or elliptical shape of its host. But in some cases, telescopes like Hubble and the Sloan Digital Sky Survey have spotted bright quasar-like objects floating off-center, sometimes far away from any galactic structure at all. This is like seeing a lighthouse shining brightly in the middle of an open ocean with no landmass anywhere in sight. Something must have sent it adrift. In a few rare cases, these quasars have been observed with measurable velocity shifts, changes in their emitted light that indicate they are moving at incredible speeds relative to their surroundings. By examining the Doppler effect in the quasar's spectrum, the stretching or squishing of light wavelengths caused by motion, scientists can estimate how fast they're traveling. Some of these objects are moving so quickly that the only plausible explanation is a massive gravitational recoil event, exactly the kind of cosmic slingshot that could launch a supermassive black hole clear out of its galaxy. Then there are the naked quasars, which seem to exist without the faint glow of starlight that would normally accompany a galaxy. This is particularly striking, because even if a galaxy were extremely faint or shrouded in dust, its stars would still produce a detectable signature. The absence of such a signature suggests these quasars have long since left their hosts behind, wandering in the dark between galaxies. Such detections are incredibly difficult, requiring deep field imaging where telescopes stare at the same patch of sky for days or weeks to gather enough light to confirm what's truly there. Or, in these cases, what's not. The existence of rogue quasars also aligns perfectly with predictions from simulations of galactic mergers and black hole dynamics. When scientists run high-powered computer models of galaxies colliding, they see scenarios where central black holes merge, emitting powerful gravitational waves. If those waves are asymmetrical, the newly formed black hole is blasted away at thousands of kilometers per second. The models show that in some cases, this ejected black hole would still be actively feeding on the gas it carried with it or on matter it encounters in its path, meaning it would appear as a bright quasar even while roaming freely in intergalactic space. These models give astronomers a kind of cosmic playbook to compare with their observations, and when the two match up, confidence grows. Another key piece of the puzzle comes from the growing ability to detect gravitational waves themselves. While we've only begun to scratch the surface with detectors like LIGO and Virgo, future space-based observatories like LISA could directly observe the kind of black hole mergers that produce ejections. If a gravitational wave event is detected and, in the years or decades afterward, astronomers find a suspiciously bright quasar far from any galaxy in the same region of the sky, it would be the smoking gun linking theory to reality. The rarity of rogue quasars doesn't make them less significant, it makes them all the more intriguing. Even a handful of confirmed examples can teach us an enormous amount about galactic evolution, the behavior of supermassive black holes, and the violent processes that can reshape the cosmos. Each one is a sort of astrophysical crime scene, where scientists sift through the clues left in light and motion to reconstruct a dramatic, almost unthinkable event, the ejection of one of the most massive objects in the universe. And while they are rare in number, the sheer vastness of the universe means that there could be countless rogue quasars roaming unseen in the deep, dark expanses between galaxies. Their rarity in our observations is partly a matter of perspective. Our telescopes, while powerful, can only survey so much of the sky at once, and many of these quasars may simply be too distant, too faint, or traveling through regions obscured by cosmic dust for us to spot them yet. The next generation of telescopes, like the James Webb Space Telescope and its successors, could dramatically increase our chances of catching these elusive wanderers in the act. Ultimately, scientists know rogue quasars exist because the universe has left a trail of breadcrumbs, displaced luminous sources, velocity shifts in their light, the absence of surrounding galaxies, and the predictive power of astrophysical models. Each clue alone might be ambiguous, but together they weave a consistent and compelling narrative, one that says these solitary, hyperactive black holes are not just the stuff of theory, but a real, if rare, part of our cosmic neighborhood. And in the quiet space between galaxies, far from the comforting glow of starlight, they continue their lonely journeys, blazing reminders that even the mightiest objects can be cast adrift. Quasar jets are among the most fearsome and awe-inspiring features in the universe, a display of raw power that can dwarf entire galaxies. Emerging from the poles of the supermassive black hole at a quasar's core, these jets are not just streams of ordinary matter, they are relativistic, meaning the particles within them are accelerated to speeds approaching the speed of light. Imagine rivers of plasma so energetic that they punch their way through interstellar and intergalactic space for millions of light years, carving cosmic highways of destruction. These are not gentle flows, they are high-energy beams capable of reshaping the very environments they pass through. If a rogue quasar wanders through the dark void between galaxies, its jets act like colossal searchlights, invisible in most wavelengths but devastating in others, sweeping through the cosmos with pinpoint lethality. The scale of these jets is staggering. Some have been measured to stretch across distances that, if overlaid on our Milky Way, would extend far beyond its boundaries, reaching into the intergalactic wilderness. The formation of these jets begins in the extreme environment around the black hole. Matter from surrounding space falls toward the accretion disk, a swirling maelstrom of superheated gas and dust spiraling inward at immense speeds. As it approaches the event horizon, magnetic fields twist and intensify, channeling some of this matter away from the disk's surface along the black hole's rotational axis. The energy involved in this process is incomprehensible. Gravitational energy from infalling matter is converted into kinetic and electromagnetic energy, launching particles outward in tightly collimated beams. These beams are so dense with energy that they can ionize gas clouds millions of light years away, leaving behind glowing filaments visible to our telescopes. And while the jets themselves are mostly invisible to the naked eye, their interactions with surrounding material cause bursts of radiation across the electromagnetic spectrum, from radio waves to deadly gamma rays. For any unfortunate star system that lies within the path of one of these relativistic jets, the results would be catastrophic. The first wave of destruction would come from the intense gamma radiation, capable of shredding atmospheres and altering the chemistry of entire planets in seconds. X-rays would follow, penetrating deep into any surviving planetary crusts and potentially sterilizing subsurface biospheres. The particle bombardment, essentially a constant rain of high-energy protons and electrons, would strip away magnetic fields, expose surfaces to direct cosmic ray impacts, and set off a chain of atmospheric loss and climate collapse. Even a planet as distant as several thousand light-years from the source could experience measurable effects over time. In fact, some scientists have speculated that gamma-ray bursts, which are similar in some respects to quasar jet emissions, may have been responsible for past mass extinction events in Earth's history. If a rogue quasar's jet ever crossed our region of the galaxy, the consequences would be many orders of magnitude more severe. One of the most fascinating, and terrifying, aspects of these cosmic death rays is their stability over time. Unlike a short-lived supernova or gamma-ray burst, which might only last seconds or minutes, quasar jets can remain active for millions, even hundreds of millions of years. That means their path through space is not a brief hazard but a long-term, sweeping scythe of destruction. As a rogue quasar drifts, its jets cut arcs across the universe, plowing through any unlucky material in their way. Given enough time, a single quasar could influence the evolution of multiple galaxies, heating intergalactic gas and preventing it from cooling into new stars. In essence, these jets can sterilize entire regions of the cosmos, creating star-forming deserts in their wake. The scale of the energy release is so extreme that comparing it to terrestrial events almost feels absurd. The combined power output of all the stars in a large galaxy is still less than what a single quasar can unleash through its jets. Each particle within the beam carries an energy far beyond anything achievable by human-made accelerators, traveling vast distances without losing much of their initial velocity thanks to the near vacuum of space. When these particles eventually collide with gas clouds or other matter, they create shockwaves that heat the surrounding gas to millions of degrees, producing enormous radio lobes that can span entire clusters of galaxies. Observations have shown that these radio lobes can persist for eons after the quasar itself has gone quiet, a lingering testament to the power of its jets. The directional nature of these jets also means that much of their lethality depends on where they are aimed. A quasar could be blindingly dangerous to any system in its line of fire, while posing minimal risk to those outside its beam's path. This anisotropy in threat level is both a blessing and a curse. It means that the universe is not uniformly hazardous. But it also means that a rogue quasar passing nearby could suddenly swing one of its jets into alignment with us. Because quasars are often powered by rotating black holes, their jet axes can wobble or precess over time, potentially sweeping across a wider swath of space. The idea that an invisible, drifting quasar could suddenly bring its beam to bear on a distant star system is one of the more chilling scenarios in astrophysics. Despite their rarity, the sheer range and influence of quasar jets mean that they play an important role in the grand-scale structure of the universe. They help regulate star formation, redistribute matter, and shape the evolution of galaxies. But when the quasar in question is a rogue, one ejected from its home galaxy and wandering freely, these same processes become untethered from the gravitational safety net of a host galaxy. The quasar's jets become a pair of unstoppable cosmic weapons, carried along with it as it drifts, potentially altering the destinies of any galaxies or systems it passes. If we were to map out all the potential paths of known rogue quasars and their jets, the universe might suddenly seem like a far more dangerous place than we tend to imagine. And perhaps the most unsettling part of all is how little warning we would have if one were headed our way. The light from a quasar can take millions or even billions of years to reach us, so by the time we detect its jets in our telescopes, their positions and directions may have changed dramatically. If a rogue quasar's beam were already on course to intersect our region of space, we might not realize it until the radiation began to arrive, and by then, any hope of shielding an entire planet from such energy would be futile. In the silent, cold vastness of intergalactic space, a rogue quasar with active jets is a predator that does not need to hunt. It simply moves, and the universe is forced to deal with the consequences of its passage. When a quasar is violently expelled from its home galaxy, the event doesn't just mark the departure of a single cosmic powerhouse. It can fundamentally alter the structure, balance, and very destiny of that galaxy. To understand the wounds left behind, imagine a city losing both its power plant and its gravitational anchor in one catastrophic instant. A supermassive black hole, especially one actively feeding as a quasar, doesn't merely sit at the center for decoration. It plays a vital role in regulating the flow of matter, the rate of star formation, and the stability of the galactic core. When it's ejected, the absence of this central mass is like removing the keystone from an arch. The stars and gas clouds closest to the center suddenly find themselves without the gravitational command they've been obeying for billions of years, and the entire inner region begins to shift, distort, and destabilize. One of the first and most dramatic scars is the sudden change in the galaxy's central gravitational potential. Before ejection, the supermassive black hole's enormous mass, often millions to billions of times that of the Sun, was anchoring the galactic core, keeping dense star clusters, gas clouds, and even smaller black holes locked in tight orbits. Once it's gone, those orbits can unravel. Some stars, freed from the grip of the central black hole, may drift outward toward the galactic halo, while others may slingshot away entirely, becoming hypervelocity stars racing into intergalactic space. The galaxy, in effect, bleeds some of its most valuable stellar material into the void. The loss of the quasar also affects the delicate feedback loop between black holes and star formation. Active supermassive black holes don't simply devour material. They also regulate the flow of cold gas in their host galaxies through powerful outflows and jets. These processes can suppress runaway star formation by heating or expelling the gas, but they can also trigger bursts of new stars by compressing gas clouds. Remove the black hole, and this feedback system collapses. Without it, the galaxy may experience uncontrolled star formation for a time, consuming its reserves of cold hydrogen far too quickly. The result is a brief but intense era of stellar birth, followed by a long, slow decline into a barren, gas-poor state. In other cases, without the quasar's influence, gas may cool and condense in chaotic, uneven patterns, creating star clusters in unusual locations and giving the galaxy an uneven, patchwork-like appearance. Another wound lies in the central structure itself. In most galaxies, the area surrounding a supermassive black hole is a dense nuclear star cluster or a compact bulge of old stars. This region is shaped not just by gravity but by the intense radiation and winds from the black hole's accretion disk. When the quasar is ripped away, the remaining central stars can be left orbiting a kind of ghost core, a dark, underdense void where once there was a gravitational monarch. Astronomers might observe such galaxies as having oddly hollow centers or disrupted bulge shapes. These structural anomalies serve as forensic evidence of a violent past, a kind of cosmic crime scene left for future civilizations, or us, to study. The path of ejection itself can also leave scars. If the quasar was expelled due to a black hole merger recoil, the gravitational wave kick would have sent shockwaves through the surrounding matter. Gas clouds could be stirred into turbulence, and magnetic fields could be twisted and reoriented. If the ejection occurred during a galactic collision, the already chaotic aftermath would be intensified by the departure of the central engine, leaving behind warped spiral arms, tidal tails, and faint streams of stars stretching into the intergalactic dark. These remnants can persist for billions of years, telling their story to anyone with the patience and telescope power to listen. Over time, the absence of the quasar can even change the fate of the galaxy itself. Without its massive anchor, the galaxy becomes more vulnerable to external gravitational influences. Passing galaxies or massive dark matter clumps can more easily tug it out of shape, distort its spiral arms, or even strip stars away. The lack of a central black hole also means there's no ultimate sink for infalling matter, so large clouds of gas may continue to swirl and collide chaotically, creating long-lived instability in the galactic core. In some cases, this instability might allow a smaller black hole or compact object to drift into the center and take the throne, but in many, the galaxy may simply limp along without a leader, slowly unraveling over cosmic timescales. From a distance, such a galaxy might look unremarkable to the casual observer, a glowing smear of light among countless others. But to trained eyes, the scars tell the story: a missing central mass, oddly distributed star populations, disrupted gas flows, and telltale streams of material marking where the quasar once reigned. These, wounded, galaxies are the galactic equivalent of an abandoned castle, still standing but forever changed by the loss of its ruler. And somewhere out in the intergalactic dark, that ruler, the rogue quasar, continues its lonely journey, feeding on whatever unlucky material crosses its path, leaving scars wherever it goes. When comparing a rogue quasar to a normal black hole, the differences are not simply in scale. They are in nature, reach, and the kind of destruction they can unleash on the universe. A normal black hole, whether its stellar mass or even a supermassive one anchored in a galaxy's core, is dangerous primarily to anything that wanders close enough to cross its event horizon or enter its strong gravitational influence. While their tidal forces, accretion disks, and relativistic jets can be extreme, their reach is usually confined to the local environment, stars, gas clouds, and perhaps nearby planetary systems in their galaxy. They can be terrifying, yes, but their influence diminishes significantly with distance. If you're a few light years away from a typical black hole, chances are you won't even notice it's there, aside from its gravitational tug. A rogue quasar, on the other hand, is the cosmic equivalent of a black hole going on an unrestrained rampage through intergalactic space. This isn't just a massive gravitational well, it's a supermassive black hole that's actively feeding on an enormous scale, converting infalling matter into mind-bending amounts of energy, and doing so while moving freely through the cosmos. The accretion disk of a quasar burns hotter and brighter than anything a normal black hole produces, outshining entire galaxies and flooding the surrounding space with deadly radiation across the electromagnetic spectrum. Where a stationary supermassive black hole in a galaxy's core has a kind of territory it affects, a rogue quasar has no such boundary. It's a mobile catastrophe, a star-eater and gas devourer with no fixed address. The destructive potential of a rogue quasar lies in its combination of mass, speed, and active feeding. A stationary quasar is bad enough, but if one is launched into intergalactic space after a black hole merger or a violent gravitational wave recoil, it becomes something entirely different, a predator on the move. Normal black holes often go unnoticed unless they are accreting matter, but a rogue quasar is, by definition, in an active state of consumption. That means blinding optical output, blazingly hot ultraviolet radiation, hard X-rays, and high-energy gamma rays pouring from its core, all of which can sterilize or destroy anything in its path over vast distances. The particle jets launched from its poles, moving at nearly the speed of light, can stretch for millions of light years and pierce through intergalactic space like lethal lances. Another stark difference is timescale. A normal stellar mass black hole can remain dormant for billions of years if there's nothing to feed on. It may be dangerous to spacecraft or wandering stars that pass too close, but its effect is mostly passive unless it finds material to devour. A rogue quasar, on the other hand, is active for tens or even hundreds of millions of years, as long as it can find enough fuel. And in its case, finding fuel is easier because it can actively seek it out by traveling through space, crossing gas-rich regions or plunging through star systems. A stationary black hole waits for victims. A rogue quasar goes hunting. Then there's the scale of the energy involved. Even the most massive stellar black hole cannot compete with the luminosity of a quasar. A single quasar can outshine 1 trillion suns, meaning its total energy output dwarfs that of any normal black hole by an astronomical margin. That energy isn't just light. It's high-energy photons and ultra-fast particles capable of eroding planetary atmospheres, stripping magnetic fields, and breaking molecular bonds in biological tissue across many light years. For life, a normal black hole might be a silent threat if approached, but a rogue quasar is an unignorable beacon of annihilation, broadcasting its lethal presence far in advance of its physical arrival. From an astrophysical standpoint, rogue quasars are also more destabilizing to cosmic structures. A supermassive black hole locked in a galaxy's core helps anchor that galaxy's gravitational structure. Remove it, especially violently, and the balance of the galaxy changes. Stars can be ejected, orbits disrupted, and the central bulge can lose cohesion. The ejected quasar carries away enormous gravitational influence, and in doing so, it leaves behind a galaxy that has been permanently altered. A normal black hole never causes such galactic-scale wounds unless it merges or feeds violently. A rogue quasar's very creation is usually the result of catastrophic galaxy-scale events, meaning its birth is inherently destructive. Finally, mobility changes the stakes entirely. A normal black hole's threat is predictable. It's where it is, and barring gravitational interactions, it stays there. A rogue quasar, moving at thousands of kilometers per second, could cross vast intergalactic distances over millions of years. That might sound slow on human timescales, but cosmically, it's fast enough to carry it into entirely new regions of the universe before its active phase ends. It's like the difference between a wildfire contained to one valley and a raging firestorm that can jump mountain ranges. One is a localized hazard, the other is a roaming catastrophe. In essence, comparing a rogue quasar to a normal black hole is like comparing a nuclear bomb to a single bullet. Both are deadly, but one is orders of magnitude more destructive, indiscriminate, and far-reaching. A normal black hole can be deadly if you wander too close, but a rogue quasar can make vast regions of the universe uninhabitable without ever having to get near you. It's the sheer combination of power, mobility, and duration that elevates rogue quasars from dangerous to apocalyptic. Out in the unfathomable darkness between galaxies, a rogue quasar drifts, appearing dormant and almost harmless to any observer, if there were any to see it. To human eyes, through even the most advanced telescopes, it might look like nothing more than a faint, barely distinguishable smudge, or perhaps disappear entirely from detection. This is because a quasar's intense brilliance comes from the process of devouring fuel, gas, dust, and stars falling into its supermassive black hole core. Without a steady supply, the quasar's light dims, its raging accretion disk cools, and its jets sputter out. But this is never the end. Rogue quasars are not dead, they are only sleeping predators, lying in wait for the next meal, and in the boundless reaches of the cosmos, time is on their side. The void between galaxies is not as completely empty as it seems. It is peppered with faint, invisible rivers of hydrogen gas, ancient globular clusters drifting like cosmic seeds, and even the occasional rogue star torn free from its galaxy's grasp. A rogue quasar may coast through these lonely expanses for millions of years before encountering such a resource, but when it does, the transformation is nothing short of cataclysmic. Imagine the black hole's gravity extending far ahead of it like an invisible net. As it approaches a sparse gas cloud, perhaps the remnant debris of a long-destroyed dwarf galaxy, its pull begins to tug on the delicate wisps of matter. Hydrogen atoms that have been floating silently for eons now find themselves drawn inward, accelerating to incredible speeds as they spiral toward the quasar's event horizon. This is the spark that reignites the beast. Friction and compression within the infalling matter generate extreme heat, and in an instant, cosmically speaking, the once dark quasar blazes back to life, its light shining so brightly that it can outshine entire galaxies again. Its accretion disk spins up to near relativistic speeds, glowing with fierce ultraviolet and X-ray radiation, while powerful magnetic fields channel enormous amounts of energy into fresh particle jets that burst forth from its poles like lances of raw destruction. The feeding frenzy can escalate rapidly. If the quasar stumbles upon a dense enough supply, such as a star cluster that has drifted too close, the results are devastating. Stars may be torn apart in a tidal disruption event, where the intense gravity rips them into streams of stellar plasma that spiral inward, each revolution unleashing more energy than a billion nuclear bombs. Entire clusters can be consumed over thousands or millions of years, their collective light replaced by the singular, terrifying beacon of the quasar's flare. For any planets that might have been orbiting these doomed stars, there would be no hope. The lethal combination of extreme radiation, relativistic jets, and gravitational chaos would sterilize them long before they could be swallowed outright. In the vast stretches between galaxies, fuel is rarer than in the bustling cores of galactic environments, but rogue quasars need not eat constantly. They only need to survive long enough to find their next meal. And unlike stars, which burn out after a finite lifetime, black holes are essentially immortal on human timescales. Even a dormant rogue quasar can drift for billions of years, crossing intergalactic gulfs and perhaps even moving from one galaxy cluster to another, waiting for just the right alignment of matter to cross its path. Its journey is slow by human reckoning but relentless in cosmic terms. Traveling at a few thousand kilometers per second, it can traverse the space between galaxies in a few 100 million years, a blink compared to the lifespan of the universe. The danger in this hunting method lies in its unpredictability. Astronomers might spot a quasar blazing far away and assume it will remain stationary, anchored to its galaxy. But a rogue quasar on the move could light up unexpectedly in what was previously considered a safe region of space. If such an event occurred closer to home, say, in the outskirts of our local group, the consequences could be catastrophic. Radiation from its reactivated core could bathe nearby galaxies in lethal energy, disrupting star formation, stripping atmospheres from planets, and altering the delicate balance of interstellar chemistry. And yet, this process of reignition is not just a destructive one, it's also a deeply mysterious clue to the nature of the cosmos. Every time a rogue quasar finds fuel and flares to life, it becomes a cosmic beacon, briefly revealing itself to astronomers across billions of light years. These sudden appearances in seemingly empty regions of the sky are some of the strongest evidence we have for the existence of these wandering giants. By studying the timing, location, and characteristics of such outbursts, scientists can map the otherwise invisible skeleton of matter that threads the universe together. The paths of these quasars may even help reveal the distribution of intergalactic gas, the hidden tendrils of the cosmic web, and the long-term evolution of galaxies themselves. A rogue quasar's reignition is a reminder that in space, death is rarely permanent. Just as stars can be born from the ashes of their predecessors, so too can a dormant black hole roar back into relevance, brighter and more destructive than ever, given the right conditions. It doesn't need to announce its presence until the moment it decides to feed, and when that happens, it's as if a lighthouse beam suddenly pierces the void, announcing to the universe that the hunter is awake again. For now, most of them sleep. But given the sheer age and size of the universe, it's only a matter of time before many more awaken, seeking sustenance in the quiet dark, and reminding us that in the cosmos, nothing truly stays quiet forever. Even in the vast emptiness of space, where most phenomena are fleeting on human timescales, a rogue quasar is a cosmic engine that can keep burning with unrelenting fury for hundreds of millions of years. This longevity is not just a side effect of its immense energy output, it is built into the very nature of what a quasar is, a supermassive black hole with an insatiable appetite and an environment that, once primed, can sustain a blazing outpouring of energy for epochs. Unlike a normal quasar anchored at the heart of its galaxy, whose fuel supply might eventually run low as its host galaxy evolves, a rogue quasar is unbound by location. It can wander through different environments over the course of cosmic history, finding multiple opportunities to refuel and flare back to life. Once set into motion, such an object can remain a hazard for almost as long as the Milky Way has existed. The first factor behind this terrifying lifespan lies in the efficiency of a quasar's energy generation. When matter spirals into a supermassive black hole's accretion disk, gravitational potential energy is converted into radiation at an efficiency far exceeding that of nuclear fusion in stars. A star like our Sun burns its fuel with about 0.7% efficiency. A quasar's accretion disk can radiate with efficiencies exceeding 10%, and in some cases, up to 40% for rapidly spinning black holes. This means that even a modest supply of matter can sustain its output for an extraordinarily long time. If the rogue quasar starts with a substantial gas reservoir, perhaps from the debris of the violent galaxy merger that ejected it, it could blaze steadily for tens of millions of years before dimming. But dimming does not mean death. Once its immediate fuel source is depleted, a rogue quasar can enter a dormant state, coasting silently through intergalactic space, effectively invisible to our instruments. This sleep mode can last for eons, but unlike a dead star, the quasar is not gone, it is merely waiting. Over cosmic timescales, it is almost inevitable that it will encounter new sources of matter, a lonely hydrogen cloud adrift between galaxies, a gas-rich dwarf galaxy unlucky enough to cross its path, or even a loose star cluster. The gravitational pull of the supermassive black hole is irresistible. Anything that comes within a certain distance will be captured, shredded, and fed to its accretion disk. This ability to turn back on, sometimes with explosive brilliance, makes the rogue quasar a repeating danger, one that can vanish from the observable universe for millions of years, only to suddenly reignite. Its potential lifespan also stems from the sheer durability of black holes themselves. These are not fragile objects. They do not burn out, decay, or suffer structural breakdowns like stars. Once formed, a supermassive black hole is effectively eternal on all practical timescales, unless the universe itself ends or it is swallowed by an even larger black hole. This means that even if a rogue quasar's active phase ends, the black hole remains fully capable of becoming active again whenever it encounters new material. A single rogue quasar could therefore have multiple reignitions over billions of years, each lasting millions of years, turning vast regions of space into deadly zones again and again. Moreover, the scale of the destruction it can cause during its long lifetime cannot be overstated. Each active episode is not just a localized hazard, it is a phenomenon capable of sterilizing entire regions of space for light years around. Planetary systems unlucky enough to be within range of its jets or radiation will be stripped of atmospheres, their surfaces scorched or irradiated beyond habitability. Star-forming regions can be disrupted, their gas blown away by the sheer force of the quasar's winds and radiation pressure. Over hundreds of millions of years, a rogue quasar could leave a trail of devastation across multiple galactic outskirts and intergalactic corridors, its destructive history written in the scars of disrupted stellar nurseries and unusually shaped gas clouds. An often overlooked implication of such longevity is that a rogue quasar we observe today may not even be in the same part of space where its destruction was originally unleashed. Because the light we see from it left millions or even billions of years ago, its actual present-day location could be hundreds of thousands of light-years away, or even in a completely different galaxy. This means our measurements are snapshots of an object in its past, and the danger it represents could now be somewhere entirely different, moving silently and invisibly toward another unsuspecting region of the cosmos. The long-active potential of a rogue quasar also has profound implications for the evolution of galaxies and the intergalactic medium. Over extended periods, the outflows and jets from such a source can inject vast amounts of energy into their surroundings, heating up intergalactic gas and preventing it from collapsing into new stars. This process, known as feedback, is thought to play a role in shaping the large-scale structure of the universe. A single rogue quasar, through repeated active phases over hundreds of millions of years, could significantly alter the developmental history of any galaxy it approaches, either by halting star formation or by triggering bursts of it through shock compression. Even in the distant future, when the universe has aged and most galaxies are dimming as their star formation ceases, rogue quasars could still be wandering, reigniting when the opportunity arises. In a sense, they could be among the last bright beacons in a fading cosmos, their destructive beauty lasting long after other luminous phenomena have faded away. For civilizations that might exist billions of years from now, these objects could still pose an existential threat, as unpredictable and unstoppable as they are today. Ultimately, the lifespan of danger posed by a rogue quasar is not a matter of years or even single geological epochs. It is measured in galactic ages. This makes them unique among cosmic hazards. Supernovae, gamma-ray bursts, and even some black hole activity are relatively short-lived events on the grand scale, their destructive phases lasting thousands or millions of years at most. A rogue quasar, by contrast, is like a predator that never dies, capable of disappearing into the void only to re-emerge again, just as deadly as before. In a universe that constantly changes, where stars are born and die, galaxies collide and merge, and entire structures shift over eons, the rogue quasar remains a constant potential threat, a cosmic wanderer with the patience to wait millions of years for its next meal, and the power to annihilate anything that strays too close. If one were headed toward our galaxy, it could pass by unnoticed for ages, dormant and dark, only to awaken when it encounters one of our outer gas clouds, lighting up once more and unleashing destruction on a scale that defies comprehension. And once active, it could remain so for longer than all of recorded human history by a factor of millions, a reminder that in the cosmic wilderness, the most dangerous predators are often the ones that never truly die. If a rogue quasar entered the Milky Way, the implications would be nothing short of apocalyptic on a galactic scale. Imagine a supermassive black hole, already a dangerous and incomprehensibly powerful entity, but one that is not sitting quietly at the heart of a galaxy. It's moving, drifting, hunting. This isn't like the supermassive black hole at the center of the Milky Way, Sagittarius A, which is largely dormant and quietly anchored in place. A rogue quasar is fully active, blazing with the energy output of trillions of suns, shooting out particle jets at nearly the speed of light, and devouring anything in its path. The moment such an object crossed into the outer halo of our galaxy, the cosmic balance we've enjoyed for billions of years would begin to unravel. At first, its arrival might not even be noticed. Space is vast, and even something as luminous as a quasar could take time before its light reaches us, especially if it approached from an angle where dust, gas, or our galaxy's own structure partially obscured it. We might first detect strange gamma-ray bursts, or a spike in X-ray emissions from an unfamiliar part of the sky. Astronomers would scramble to triangulate the source, but by the time we realized it was heading toward the Milky Way, it could already be deep inside the galactic halo, altering the delicate gravitational structure that holds stars in their orbits. As it moved inward, the rogue quasar would begin interacting with the interstellar medium, the sparse gas and dust that float between stars. This material would act as fuel, feeding the quasar's accretion disk and keeping it burning bright. The swirling disk of plasma around its black hole would glow across the electromagnetic spectrum, making it a beacon visible from billions of light years away. But for us, it would be more than a beautiful object. It would be a predator entering a pasture full of prey. Every star, every gas cloud, every planet in its path would either be consumed or blasted by lethal radiation. One of the most devastating effects would come from the quasar's relativistic jets. If one of these jets happened to be aimed even partially in our direction, it would unleash a constant stream of high-energy particles, gamma rays, and X-rays capable of stripping atmospheres from planets across thousands of light years. Earth's magnetic field and atmosphere, which normally shield us from cosmic rays, would be no match for the sheer energy output of a quasar jet aimed directly at us. Even if we were far from the quasar's center, being in the line of fire could sterilize our planet's surface, destroy the ozone layer, and trigger mass extinctions. The gravitational influence of a rogue quasar would also be catastrophic. A supermassive black hole millions or even billions of times the mass of the Sun passing through our galaxy would distort stellar orbits, destabilize star systems, and fling planets into interstellar space. Star clusters could be ripped apart. Entire streams of stars might be thrown into the void as the quasar's immense gravity plows through the galactic disk like a bowling ball scattering pins. If it passed anywhere near our solar system, within a few light years, it could disrupt the Oort cloud, sending a deadly rain of comets toward the inner planets. The regions closest to the quasar's path would be annihilated. Stars unfortunate enough to wander too near would be torn apart by tidal forces, their matter spiraling into the accretion disk, releasing bursts of energy far beyond anything our Sun could produce. This process would trigger more intense radiation events, creating localized, death zones, where no life could survive. The quasar's movement would leave a scar through the Milky Way, an elongated trail of disrupted gas, dead stars, and irradiated worlds. Even regions far from its direct path would not be safe. The sheer brightness of a quasar can overwhelm the night sky across an entire galaxy. The energy it releases in ultraviolet and X-ray wavelengths would ionize vast amounts of interstellar gas, altering star formation rates. Instead of being a place where stars are born, the regions near the quasar could become barren and hostile. The quasar's influence could even heat and disperse entire molecular clouds, preventing them from collapsing into new stars for millions of years. If the rogue quasar lingered in our galaxy, feeding on its resources, the Milky Way could be permanently altered. Over time, it might strip away enough material to change the galaxy's shape and dynamics. It could create vast cavities in the interstellar medium, disrupt spiral arm structures, and even trigger chain reactions of supernovae as stars near the quasar's jets become destabilized. The long-term result could be a Milky Way that is dimmer, less fertile for star and planet formation, and littered with dead zones, places where radiation still lingers long after the quasar has moved on. The most terrifying part: we might not even be able to predict exactly where it would go. The quasar's path would depend on its original ejection velocity, gravitational interactions with other massive objects, and the structure of our galaxy itself. Even if we knew it was coming decades or centuries in advance, there would be nothing we could do to stop it. Humanity's best hope would be to find some way to flee, perhaps to an entirely different galaxy. But given the speeds and distances involved, such an escape would be far beyond our current technological capabilities. And yet, in a strange way, the entry of a rogue quasar into the Milky Way would be an awe-inspiring event. For astronomers, it would be a once-in-a-universe observational opportunity, a front-row seat to one of the most extreme phenomena nature can produce. We would be able to watch, in real time, how a quasar interacts with a living galaxy, how it feeds, how it alters the cosmic landscape. But for life on Earth and countless other worlds, it would almost certainly mark the beginning of the end. If such an event were unfolding right now, somewhere far away on the other side of our galaxy, the light from it might already be traveling toward us. We just wouldn't know, until one day, a new, impossibly bright object appears in our sky, outshining everything except the sun and moon. And by then, the countdown to our annihilation would already have begun. Even when a rogue quasar's brilliant light dims or its blazing jets fall silent, its massive presence remains an invisible but devastating force in the cosmos. This enduring influence is rooted in gravity, the fundamental force that shapes the universe and governs the motion of stars, planets, and galaxies alike. Unlike radiation or electromagnetic signals, which travel at the speed of light and can be blocked or absorbed, gravity is omnipresent and relentless. It cannot be switched off or hidden. A supermassive black hole, rogue or otherwise, wields an overwhelming gravitational pull that extends far beyond its glowing accretion disk, capable of disturbing the orbits of countless stars even when it appears invisible to telescopes. When a rogue quasar drifts into a galaxy, whether the Milky Way or a distant spiral, it carries with it an immense mass, often millions or billions of times that of our Sun. This mass warps the fabric of space-time, creating a gravitational well so deep that objects passing near it are forced into new trajectories. Unlike stars or planets, which have relatively modest gravitational effects compared to a supermassive black hole, a rogue quasar can bend the orbits of entire star systems, shift the paths of interstellar gas clouds, and distort the very shape of the galaxy's disk and halo. These effects unfold silently and invisibly over hundreds of thousands or millions of years, making the rogue quasar a stealthy disruptor. Consider a star in the outer reaches of a galaxy orbiting peacefully around the galactic center. The arrival of a rogue quasar changes everything. The black hole's gravity can pull the star off its regular path, altering its velocity and orbital eccentricity. In some cases, stars might be flung outward, becoming hypervelocity stars that escape the galaxy entirely, racing into intergalactic space at hundreds or thousands of kilometers per second. Others may be pulled inward, spiraling dangerously close to the quasar's event horizon, destined to be torn apart by tidal forces. In this way, a rogue quasar acts like a cosmic wrecking ball, rearranging the architecture of the galaxy piece by piece. This gravitational influence extends beyond individual stars to entire star clusters and molecular clouds. Dense clusters that once moved in stable orbits can be stretched and pulled apart, their stars scattered into loose associations or ejected entirely. Gas clouds, the birthplaces of new stars, can be compressed or dispersed, affecting the future star formation rate of the galaxy. Regions once fertile with potential are rendered barren or unstable. Over time, the rogue quasar can sculpt the galaxy's morphology, making spiral arms warp or dissolve, thickening the galactic disk, or creating tidal streams of stars trailing behind it. What makes this invisible influence especially menacing is that it can be nearly impossible to detect before catastrophic damage occurs. Unlike bright electromagnetic emissions that announce the presence of an active quasar, a dormant rogue black hole traveling through the galaxy emits little to no light. Without the telltale signs of accretion, it can drift unnoticed for millions of years, gradually distorting orbits and sowing chaos silently. Astronomers rely on indirect methods to detect such gravitational interlopers, monitoring stellar motions for anomalies, mapping the distribution of gas and stars for unexpected perturbations, and searching for hypervelocity stars that may have been ejected by close encounters. The subtle but powerful effects of this gravitational influence can ripple through an entire galaxy. The redistribution of stellar orbits affects the dynamics of galactic rotation, potentially altering the balance between dark matter, stars, and gas. It can even influence the trajectory of satellite dwarf galaxies, changing the way they interact and merge with the larger host galaxy. This ongoing gravitational turmoil might trigger new waves of star formation in some regions while quenching it in others, depending on how gas clouds are compressed or dispersed. A rogue quasar's mass can also disrupt the orbits of planets within star systems, especially those in multi-star or loosely bound systems. Small shifts in stellar motion can destabilize planetary orbits, causing them to become highly elliptical, or even ejecting planets entirely into the cold abyss of space. For any planets still harboring life, these orbital disruptions could mean catastrophic climate changes, increased radiation exposure, or complete loss of a stable orbit around their host star, effectively ending their habitability. Moreover, the gravitational pull of a rogue quasar can trigger complex gravitational interactions known as three-body problems when it encounters star systems or clusters with multiple massive bodies. These chaotic interactions often result in unpredictable outcomes. Stars may be exchanged between systems, orbits altered beyond repair, and objects catapulted out at high velocities. Such processes can reshape not only the immediate vicinity of the quasar but also more distant regions of the galaxy through gravitational resonance effects. Even when a rogue quasar passes far from a galaxy's luminous core, its massive presence can induce waves in the galaxy's dark matter halo, the mysterious and invisible scaffolding that holds galaxies together. These gravitational disturbances may ripple through the halo, altering the distribution of dark matter and potentially affecting the overall gravitational potential of the galaxy. Although dark matter itself doesn't interact electromagnetically, its gravitational influence is critical to galaxy stability. A rogue quasar's passage might trigger long-lasting changes in this invisible framework, compounding the galaxy's instability over millions of years. The gravitational influence of a rogue quasar is also a major concern for the large-scale structure of the universe. Galaxies don't exist in isolation. They are part of clusters and superclusters connected by vast filaments of dark matter and gas. When a rogue quasar moves through these structures, its gravity can alter the flow of matter along cosmic filaments, potentially influencing the rate at which galaxies merge, gas cools, or stars form on a grand scale. It is a reminder that the universe is a dynamic web of interactions, where even a single massive object can have outsized effects. In short, even when a rogue quasar is invisible, dormant, or seemingly inert, it remains a gravitational titan with the power to rewrite the destinies of stars, planets, and entire galaxies. Unlike its luminous, fiery phase, this silent stage of influence is harder to detect but just as destructive, working patiently over millennia to destabilize cosmic neighborhoods. It is a ghostly force, lurking unseen but shaping the universe in profound and lasting ways. Hunting rogue quasars presents one of the most daunting challenges in modern astrophysics. These celestial nomads, drifting untethered through the vast expanses between and within galaxies, are by nature elusive. They can lurk in the shadows, their brilliant light extinguished temporarily by a lack of fuel, or hidden behind thick cosmic dust. Detecting them requires a blend of cutting-edge technology, clever methodologies, and years of patient observation. Astronomers employ a combination of sky surveys, redshift analysis, and indirect missing galaxy checks to identify these objects that refuse to stay put. One of the primary tools in this search is wide-field sky surveys, massive programs that systematically scan huge swaths of the sky across multiple wavelengths, from visible light to radio waves, X-rays, and gamma rays. Projects like the Sloan Digital Sky Survey (SDSS), the Panoramic Survey Telescope and Rapid Response System (PanSTARRS), and upcoming observatories such as the Vera C. Rubin Observatory generate terabytes of data daily, capturing billions of celestial objects. Within this ocean of data, astronomers sift for anomalies, sources of intense energy that do not conform to known patterns of galaxies or stars. Rogue quasars, Because they are bright and energetic but lack an obvious host galaxy, stand out as orphan light sources drifting in apparent isolation. A key method used to distinguish rogue quasars from other bright objects involves redshift analysis. Redshift refers to the stretching of light waves toward the red end of the spectrum due to the expansion of the universe, or the relative motion of celestial bodies. By measuring the redshift of a quasar's light, astronomers can determine how fast it is moving away from us and estimate its distance. For typical quasars residing in galactic centers, their redshift matches the expected values for their galaxy. However, rogue quasars may exhibit peculiar redshifts inconsistent with the location of nearby galaxies or galaxy clusters. A quasar whose redshift places it at a different velocity or distance than its nearest neighbors is a prime candidate for being rogue, ejected, and traveling alone through intergalactic space. Spectral analysis further aids in this identification. Quasars have distinctive emission lines caused by highly ionized atoms in their accretion disks. These spectral fingerprints allow astronomers to differentiate quasars from stars, galaxies, or other energetic sources like supernovae or gamma-ray bursts. By comparing the spectra to databases of known objects, researchers can spot quasars that don't seem to be anchored to any visible galaxy. Such hostless quasars raise immediate red flags as potential rogues. Another fascinating approach is the so-called missing galaxy check. Because a quasar's incredible luminosity often outshines its host galaxy's stars, the galaxy may be hard to see directly. However, astronomers use deep imaging techniques and infrared observations to detect the faint glow of the galaxy's stellar population, even when obscured by dust or overwhelmed by the quasar's light. When a luminous quasar appears with no detectable host galaxy despite deep imaging, it may indicate that the quasar has been ejected entirely, now drifting alone without the gravitational cradle of its original galaxy. Confirming this requires painstaking observation across multiple wavelengths, often using the world's most powerful telescopes such as the Hubble Space Telescope, the Very Large Telescope, VLT, or the Atacama Large Millimeter/Submillimeter Array, ALMA. Astronomers also look for indirect evidence in the form of galactic wounds. When a supermassive black hole is ejected from a galaxy, it leaves behind scars, disturbed stellar orbits, unusual gas dynamics, and asymmetries in the galaxy's shape. By mapping these distortions with precise measurements of star velocities and gas distribution, researchers can infer the past presence of a rogue quasar. This forensic approach allows scientists to find the cosmic crime scene even when the culprit is far away. Monitoring high-energy emissions in X-rays and gamma rays is crucial, too. Rogue quasars are prolific producers of these energetic photons, and space telescopes like the Chandra X-ray Observatory and the Fermi Gamma Ray Space Telescope scan the skies for transient or persistent sources without clear galactic hosts. Unidentified high-energy sources with quasar-like spectra may be hidden rogues awaiting confirmation. Gravitational wave astronomy, still in its infancy but rapidly advancing, adds another dimension to this hunt. When two supermassive black holes merge, a likely precursor to rogue quasar ejection, they produce gravitational waves rippling through spacetime. Detecting these waves with observatories like LIGO, Virgo, or the future space-based LISA, Laser Interferometer Space Antenna, can alert astronomers to recent black hole mergers, hinting at places where rogue quasars might be born or ejected. Combining gravitational wave data with electromagnetic observations helps narrow down candidate regions for closer study. Machine learning and artificial intelligence have become invaluable in this quest. The sheer volume of data from sky surveys is beyond the capacity of human analysts alone. Advanced algorithms trained on known quasar features can scan images and spectra for subtle signs of rogue behavior, such as unusual motion, brightness fluctuations, or spectral anomalies, flagging candidates for follow-up observation. These techniques increase the efficiency and accuracy of identifying rogues hidden in vast datasets. Despite these powerful tools, hunting rogue quasars remains extraordinarily challenging. Their rarity means few examples exist for comparison, making it hard to define a typical rogue quasar signature. Their potential to be dormant for long periods further complicates detection, as they might only briefly flare when encountering fresh fuel. Moreover, the immense distances involved mean the light we see from them left millions or billions of years ago. Sometimes the rogue quasar itself may have moved far from where we observe it, or even died out after a last flare. Still, every confirmed detection is a triumph that reshapes our understanding of galaxy evolution, black hole physics, and cosmic dynamics. Each newly discovered rogue quasar is like a piece of a vast jigsaw puzzle, helping to fill in the picture of how black holes influence their environments, how galaxies grow and change, and how matter and energy move through the universe. The search continues with ever more powerful telescopes, larger sky surveys, and increasingly sophisticated data analysis methods. Future observatories such as the James Webb Space Telescope, the Square Kilometre Array, and next-generation gravitational wave detectors promise to deepen our view and perhaps reveal many more of these cosmic wanderers. As technology advances, the hidden predators of the cosmos, the rogue quasars, may become less mysterious, allowing us to better predict their behavior, track their movements, and perhaps one day understand how to coexist with these titans of destruction in the grand cosmic dance. Throughout decades of observations, astronomers have identified a handful of intriguing objects that exhibit many of the defining characteristics expected of rogue quasars. These candidates are cosmic enigmas, sources of tremendous energy that seem to defy the norms of quasar behavior by lacking clear host galaxies or appearing to move independently through intergalactic space. While no definitive rogue quasar has yet been confirmed beyond all doubt, these objects provide tantalizing glimpses into the possible lives of such cosmic wanderers, and studying them sheds light on the processes that might create or sustain rogue quasars across the universe. One of the most famous candidates is the quasar He 0450-2958, sometimes called the naked quasar. Discovered in the early 2000s, this quasar sits roughly 2 billion light-years from Earth, shining with the brightness of a trillion suns. What makes He 0450-2958 remarkable is the apparent absence of any host galaxy around it, despite deep imaging with the Hubble Space Telescope and other powerful instruments. Normally, quasars reside at the centers of galaxies where they feast on gas funneled toward the central supermassive black hole. But this quasar appeared to be floating alone, leading astronomers to hypothesize that it might be a supermassive black hole ejected during a violent galactic collision. Supporting this theory, observations revealed a disturbed galaxy near the quasar, suggesting that interactions between galaxies could have violently expelled the black hole from its home. Although follow-up studies have debated whether the host galaxy is simply faint or obscured, He 0450-2958 remains one of the most compelling examples of a quasar possibly adrift without a home. Another notable example is the quasar SDSS J0927+2943, located about 5 billion light-years away. This quasar's light spectrum exhibits unusual shifts indicating it might be moving rapidly relative to nearby galaxies. Some researchers interpret these velocity offsets as signs that the supermassive black hole at its center was given a gravitational kick, likely from the merger of two massive black holes, propelling it away from its host galaxy. The phenomenon is consistent with predictions from general relativity about the recoil effect caused by asymmetric emission of gravitational waves during black hole mergers. If confirmed, this would make SDSS J0927+2943 a textbook case of a rogue quasar in motion. Its discovery was groundbreaking because it provided a direct observational link between gravitational wave physics and the large-scale dynamics of quasars and galaxies. A further fascinating candidate is the object known as CID-42, found within the Cosmos Survey, which examines a large patch of the sky with multi-wavelength imaging and spectroscopy. CID-42 exhibits signs of a recoiling supermassive black hole, with observations indicating two compact X-ray sources in close proximity, possibly a black hole merger in progress, or an ejected black hole moving away from its original host galaxy. The system shows dramatic velocity differences between gas and stars, which could only be explained by a black hole displaced from its galactic nucleus. Although alternative explanations exist, such as binary black hole systems, CID-42's characteristics align well with theoretical models of rogue quasar formation. In the radio wavelength regime, astronomers have spotted several jet-producing sources that seem to lack clear galactic hosts. These orphan jets emit powerful streams of relativistic particles into space but are not associated with any visible galaxy or star cluster. The nature of these jets suggests the presence of a supermassive black hole, possibly a rogue quasar, moving through intergalactic space. Because radio waves can penetrate cosmic dust that obscures optical observations, these detections are valuable clues that rogue quasars might be more common than visible light surveys suggest. In addition to these specific candidates, large-scale sky surveys continually uncover objects with peculiar properties, bright point sources with spectral features of quasars but without clear galactic context. These candidates are often flagged for follow-up studies using spectroscopy, multi-wavelength imaging, and high-resolution astrometry to confirm their nature and possible rogue status. Some might be quasars with host galaxies too faint or too obscured to detect with current technology, while others may indeed be the long-sought rogues drifting between galaxies. As the field advances, gravitational wave astronomy adds an exciting dimension. The detection of mergers between supermassive black holes, expected to be a key mechanism in producing rogue quasars, can help pinpoint where and when such objects might be born. Future gravitational wave observatories like LISA will provide detailed maps of these cosmic collisions, guiding electromagnetic observations to candidate rogue quasars shortly after their ejection. It is important to emphasize that the rogue quasar phenomenon is still a frontier of astrophysical research. Each candidate challenges our understanding of black hole physics, galaxy evolution, and cosmic dynamics. The rarity of confirmed examples is partly due to the difficulty of observing such objects. They are transient in nature, may be obscured, or simply too distant and faint for current instruments. As telescopes grow more powerful and data analysis techniques improve, astronomers expect the number of candidates to increase, sharpening the picture of how these cosmic nomads form, behave, and influence their environments. Ultimately, these known candidates provide critical test cases to refine theoretical models. By studying their spectra, luminosity, motion, and surrounding environments, scientists gain insights into the violent processes that eject quasars from galaxies, the conditions that allow them to survive and feed in isolation, and the long-term consequences of their journeys. These rogue quasars are not just astrophysical curiosities. They are keys to understanding some of the most extreme and energetic events shaping the universe. When comparing rogue quasars to supernovae, it quickly becomes clear why rogue quasars represent a far more menacing and persistent cosmic threat. Both phenomena are among the most powerful and energetic in the universe, capable of unleashing enormous quantities of radiation and matter. Yet their scales of destruction, durations, and overall impact on their cosmic neighborhoods differ radically, placing rogue quasars in a class of danger that dwarfs even the most violent stellar explosions. Supernovae are spectacular events, the final death throes of massive stars, that release as much energy in a matter of weeks or months as the Sun will emit over billions of years. Their brilliant explosions briefly outshine entire galaxies, sending shockwaves and streams of high-energy particles rippling through space. They are responsible for forging heavy elements critical for planet formation and life itself, seeding the cosmos with the building blocks of chemistry. While their role in the cosmic ecosystem is essential, supernovae are comparatively brief and localized events. Rogue quasars, in contrast, are engines of destruction on an almost incomprehensible scale that lasts orders of magnitude longer. A single rogue quasar, powered by a supermassive black hole with millions to billions of solar masses, can shine with the luminosity of trillions of suns for hundreds of millions of years. This sustained brilliance is sustained by matter spiraling into the black hole's accretion disk, releasing radiation and energetic particle jets at near light speeds. One of the starkest contrasts lies in their spatial reach. A supernova's blast radius, where its radiation and shockwaves can sterilize planets or disrupt star-forming regions, typically extends for tens to a few hundred light-years. Within this zone, the intense gamma rays and cosmic rays can strip atmospheres, induce mass extinctions, and alter the chemistry of planetary environments. However, beyond this radius, the supernova's effects sharply diminish, leaving distant regions of the galaxy largely untouched. Rogue quasars, by contrast, affect regions spanning thousands to tens of thousands of light-years. Their ultra-powerful radiation fields and relativistic jets can flood entire galactic sectors with lethal doses of gamma rays, X-rays, and particle bombardment. Planets tens of thousands of light-years away, normally safe from most energetic events, could fall within a rogue quasar's death zone. This immense reach arises from the quasar's sustained output and the focused nature of its jets, which channel destructive energy along narrow beams that pierce through interstellar and intergalactic space over millions of light-years. Persistence is another key factor. While a supernova's energy output declines rapidly after the initial explosion, becoming a fading remnant within a few thousand years, a rogue quasar's active phase can endure for tens to hundreds of millions of years. This longevity means the destructive influence of a rogue quasar is not a brief cosmic flash but a persistent storm, continuously irradiating, heating, and disrupting its surroundings. Over such extended timescales, the quasar's effects accumulate, reshaping entire regions of a galaxy's structure and chemistry, inhibiting star formation, and sterilizing vast volumes of space repeatedly. The frequency and rarity of these events also shape their threat levels differently. Supernovae are relatively common in active star-forming galaxies like the Milky Way, occurring roughly once every 50 years. Their predictable presence and distribution mean advanced civilizations could theoretically anticipate and adapt to such risks by detecting impending supernova candidates or migrating away from vulnerable regions. Rogue quasars, on the other hand, are exceedingly rare and far less predictable. Their sudden appearance, sometimes invisible until active, and potential to drift silently through intergalactic space make them more insidious. In terms of direct threat to planetary systems, a nearby supernova can devastate life on a planet within its blast radius but leaves distant star systems largely untouched. A rogue quasar traveling through or near a galaxy, however, has the potential to devastate multiple star systems along its path, changing the habitability of entire galactic sectors over millions of years. Its jets and radiation fields can sterilize regions that would otherwise remain safe, and its gravitational influence can destabilize planetary orbits, causing cascading effects on planetary climates and biospheres. Moreover, the impact of a supernova, while dramatic, is generally a one-off event. Rogue quasars can reignite multiple times as they encounter new gas clouds and star clusters, prolonging their destructive reign across cosmic epochs. This repeated activity makes rogue quasars dynamic hazards, capable of initiating multiple waves of devastation and alteration wherever they wander. The environmental consequences also differ markedly. Supernovae enrich the interstellar medium with heavy elements, catalyzing the chemical complexity necessary for planets and life. Rogue quasars, by contrast, tend to inhibit star formation. Their intense radiation heats and disperses gas clouds, blowing away the raw materials needed for new stars. This feedback can suppress the growth of galaxies, fundamentally altering their evolution and making rogue quasars powerful agents of cosmic regulation. On a galactic scale, rogue quasars are capable of driving feedback mechanisms that govern the growth of supermassive black holes and their host galaxies. By ejecting gas and heating the surrounding medium, they can prevent runaway star formation and influence the distribution of dark matter and baryonic matter in their vicinity. These long-term effects are profound, making rogue quasars key players in cosmic evolution. In summary, rogue quasars are scarier than supernovae because their destructive range is vastly larger, their active lifespans far longer, and their potential to repeatedly disrupt galactic ecosystems much greater. While supernovae blaze brightly and briefly, rogue quasars persist as deadly cosmic predators, drifting silently through space, capable of rewriting the fates of stars, planets, and entire galaxies. Their sheer scale, power, and longevity make them one of the universe's most formidable and least understood threats. Determining a safe distance from a rogue quasar involves navigating the interplay of immense energies, relativistic particle jets, and gravitational influence that define these cosmic giants. Unlike more familiar astronomical threats, such as supernovae or gamma-ray bursts, whose danger zones are relatively well understood, rogue quasars are far more complex due to their enormous scale, longevity, and variability. The question of how far away a planet, star system, or even a galaxy must be to avoid the lethal effects of a rogue quasar is not a simple matter of fixed numbers. It depends on numerous factors including the quasar's luminosity, jet orientation, surrounding environment, and the nature of the cosmic medium through which its radiation and particles travel. To start with, the absolute luminosity of a typical quasar is staggering. Quasars can radiate energy equivalent to the light output of trillions of suns, with bolometric luminosities often exceeding 10 to the power of 39 watts. This radiation spans a broad range of the electromagnetic spectrum, from radio waves to high-energy gamma rays, and it is the high-energy portion, particularly X-rays and gamma rays, that pose the greatest hazard to life and matter. For context, Earth's biosphere is protected from most harmful cosmic radiation by our atmosphere and magnetosphere. However, these defenses are only effective against typical cosmic rays and solar flares. The intense, focused emissions from a quasar's jets or its extreme ultraviolet and X-ray radiation can overwhelm planetary shields across vast distances. If a rogue quasar's relativistic jets were to point directly at a planet, the lethal radiation flux could sterilize the planet's surface from tens of thousands of light-years away. The reason is twofold. Relativistic jets concentrate energy into narrow beams, dramatically increasing radiation intensity along their paths, and the particles and photons travel near the speed of light, delivering a concentrated dose of ionizing radiation capable of stripping atmospheres, destroying ozone layers, and causing widespread molecular damage. However, because these jets are narrowly focused, their destructive cones cover only a small fraction of the sky at any given moment. For planets outside the jet's direct line, radiation hazards come from the quasar's accretion disk and surrounding emissions, which, while still incredibly powerful, are more isotropic and thus spread over a larger area, reducing intensity with distance. Scientists estimate that the lethal zone for a quasar's radiation, where it can cause biological sterilization or severe atmospheric damage, can extend up to several thousand light-years from the source, depending on jet orientation and intrinsic luminosity. For example, a quasar with luminosity around 10 to the power of 39 watts might sterilize planets within 5,000 to 10,000 light-years if they lie within the jet's beam. Outside the jets, the safe distance increases, but harmful radiation can still affect regions up to a few hundred to 1,000 light-years away. The gravitational influence of a rogue quasar also factors into safety considerations. Even if radiation does not reach a planet in lethal doses, the black hole's immense gravity can destabilize stellar orbits from much greater distances. This gravitational reach can span tens of thousands of light-years, particularly if the quasar passes close to the dense stellar regions of a galaxy. For planetary systems, significant perturbations can occur within a few light-years, potentially ejecting planets or altering their climates by changing their orbits around host stars. The threat is amplified by the longevity of rogue quasars. Unlike transient events, such as supernovae that last weeks or months, a rogue quasar can remain active and hazardous for hundreds of millions of years. This persistence means that the safe distance is not just about instantaneous exposure, but prolonged effects. Continuous bombardment of radiation over millions of years can slowly erode atmospheres, increase mutation rates in organisms, and destabilize complex ecosystems even at distances initially deemed safe. Another critical factor is the density and composition of the interstellar and intergalactic medium between the quasar and potential targets. Dust and gas clouds can absorb and scatter radiation, providing some shielding, but high-energy gamma rays and relativistic particles can penetrate or bypass such obstacles. Additionally, interactions with interstellar magnetic fields can deflect charged particles, altering the distribution of cosmic rays but also potentially channeling them into localized hot spots. Given these complexities, astronomers use computational models to simulate the impact zones of quasars under various conditions. These simulations incorporate radiation intensity, particle flux, jet dynamics, gravitational effects, and environmental factors to estimate hazard distances. The results vary depending on quasar type, black hole mass, accretion rate, and jet orientation. For a typical rogue quasar, a conservative estimate of the minimum safe distance, where biological life could persist without catastrophic radiation exposure and gravitational disruption, might lie around 10,000 to 20,000 light-years from the quasar's core, assuming the planet is outside the direct path of its jets. Within this radius, the risk of atmospheric stripping, sterilization, and orbital instability increases dramatically. In regions densely packed with stars, such as galactic centers or starburst clusters, the presence of a rogue quasar would be especially devastating. The safe zones would shrink considerably because overlapping gravitational and radiation effects could compound. Conversely, in the sparse intergalactic voids, the lack of nearby material to feed the quasar might reduce its activity and radiation output, extending the safe distance. Importantly, safety distances are not fixed and evolve as the rogue quasar moves through space. As it encounters fresh gas clouds or star clusters, its accretion rate, and thus luminosity, can spike, expanding its lethal radius. Likewise, as it consumes available fuel or moves into lower density regions, its emissions may wane, temporarily reducing its hazard footprint. For our own Milky Way, estimates suggest that if a rogue quasar approached closer than about 15,000 light-years, roughly halfway to the galactic center from the Sun, it would begin to pose significant risks to Earth and the solar system. Within 5,000 light-years, catastrophic consequences would be almost certain, including sterilization of life on Earth, destabilization of planetary orbits, and widespread disruption of the galactic environment. The vastness of space offers a natural buffer, making encounters with rogue quasars statistically rare. Nevertheless, the possibility that one might one day enter our galactic neighborhood underscores the importance of monitoring and understanding these cosmic predators. The ongoing search for rogue quasars and careful study of their properties contribute not only to astrophysics but to planetary defense on an unimaginably large scale. In conclusion, while exact, safe distances vary depending on a rogue quasar's power and orientation, the minimum range to avoid lethal radiation and gravitational chaos spans tens of thousands of light-years. The immense scale of these objects means that their influence extends far beyond the reach of most known cosmic hazards, making them uniquely dangerous in the universe's vast theater. When comparing rogue quasars and gamma-ray bursts, GRBs, we encounter two of the universe's most formidable and violent phenomena, each capable of unleashing staggering amounts of energy capable of devastating their cosmic neighborhoods. Yet despite some superficial similarities, immense power, lethal radiation, and potential for mass destruction, these two cosmic killers differ fundamentally in their nature, timescale, mechanisms, and the breadth of their destructive influence. Understanding these differences is essential for appreciating why rogue quasars pose a unique, persistent threat compared to the relatively brief but intense blasts of GRBs. Gamma-ray bursts are brief, extraordinarily intense flashes of gamma radiation detected by space-based observatories. They are among the most luminous electromagnetic events known, capable of releasing as much energy in seconds as the Sun will emit over its entire 10 billion-year lifespan. GRBs typically last from milliseconds to several minutes, though some rare, ultra-long bursts can persist for hours. They are generally classified into two main categories: short-duration GRBs, believed to result from the merger of compact objects such as neutron stars, and long-duration GRBs, associated with the collapse of massive stars into black holes and supernova explosions. Rogue quasars, on the other hand, are not transient flashes but continuous engines of high-energy radiation fueled by the accretion of gas and dust onto a supermassive black hole. These black holes can be millions or billions of times the mass of our Sun, located far from the center of any galaxy, wandering through intergalactic or galactic space as gravitational exiles. Unlike GRBs, which are typically one-time explosive events, rogue quasars shine for millions to hundreds of millions of years, maintaining a sustained output of radiation and relativistic particle jets. One of the most striking differences lies in their timescales. GRBs, as intense as they are fleeting, transient bursts lasting minutes or less. Their impact is devastating but momentary. The radiation arrives in a focused, extremely energetic beam, often narrow and tightly collimated, capable of causing catastrophic damage within a few thousand light-years but dissipating quickly as the burst ends. Rogue quasars, by contrast, are persistent. Their powerful jets and accretion disk emissions can irradiate entire regions of a galaxy continuously over geological timescales, steadily eroding atmospheres, disrupting star formation, and destabilizing planetary systems. The spatial scale of their influence also differs. GRBs typically affect zones spanning a few thousand light-years, where their intense gamma-ray and cosmic ray emission can sterilize life and damage atmospheres. Their radiation is highly directional, like a cosmic laser pointer, so the destructive path is limited to a narrow cone. Rogue quasars can influence vast volumes of space, from thousands up to tens of thousands of light-years in radius, depending on their luminosity and jet structure. Unlike GRBs, which are brief, quasars maintain their lethal radiation fields and particle jets over millions of years, amplifying their cumulative damage and expanding their impact zones. Mechanistically, GRBs arise from catastrophic events marking the death or collision of compact objects, releasing gravitational energy almost instantaneously as gamma radiation. The physical process involves ultrarelativistic jets piercing through collapsing stars or merger debris, producing shockwaves that accelerate particles to extreme energies. These jets generate intense gamma rays that blast through surrounding space, their energy concentrated into narrow beams. Rogue quasars, however, owe their power to the steady infall of matter into a supermassive black hole's accretion disk. As gas spirals inward, it heats to millions of degrees, radiating enormous energy across the electromagnetic spectrum, from radio waves to X-rays and gamma rays. Magnetic fields near the black hole's event horizon channel some of this energy into twin relativistic jets launched perpendicular to the accretion disk. Unlike the short-lived GRB jets, quasar jets are persistent and can extend millions of light-years into intergalactic space. Their origins also shape their distribution and detectability. GRBs can occur anywhere massive stars exist or where compact objects collide, including within star-forming regions of galaxies. Rogue quasars are tied to the fate of supermassive black holes, often birthed during violent galaxy mergers that eject black holes from their galactic centers. As such, they may wander in relatively empty intergalactic spaces or in the outskirts of galaxies, making them harder to locate and study. The impact on life and planetary systems differs notably. A GRB aimed directly at Earth would deliver a lethal dose of gamma radiation within seconds, potentially destroying the ozone layer, causing mass extinctions, and irradiating the surface. Such an event is catastrophic but instantaneous, with lingering biological effects spanning centuries or millennia. The rarity and unpredictability of nearby GRBs make them a feared but statistically unlikely threat. Rogue quasars pose a subtler, more insidious threat. Their continuous radiation can erode atmospheres and irradiate planets over millions of years, potentially preventing life from developing or surviving in entire galactic regions. Their gravitational influence can destabilize orbits over long timescales, gradually reshaping star systems. Rogue quasars are thus chronic cosmic predators, shaping galactic environments persistently, unlike the explosive one-off blasts of GRBs. From an observational standpoint, GRBs are easier to detect due to their brightness and transient nature. Space telescopes designed for gamma-ray astronomy, like NASA's SWIFT and Fermi, can locate GRBs within seconds, allowing rapid follow-up observations. Rogue quasars require long-term monitoring across multiple wavelengths and sophisticated analysis to identify their wandering signatures, especially when inactive or obscured. In summary, gamma-ray bursts are violent, sudden, and narrowly focused cosmic blasts that deliver immense energy in brief moments, posing acute but short-lived dangers. Rogue quasars are colossal, enduring beacons of destruction, radiating intense energy continuously for millions of years, reshaping galaxies and irradiating large volumes of space with persistent, multi-wavelength fury. Their destructive scales and mechanisms differ fundamentally, making each uniquely dangerous in its own cosmic context. Understanding both enhances our grasp of the universe's most extreme processes and the threats they pose to life and structure across cosmic time. The arrival or approach of a rogue quasar toward our cosmic neighborhood would not go unnoticed by astronomers equipped with the right tools and knowledge, at least in principle. Though these hyperactive supermassive black holes drift silently and invisibly across vast distances, their immense energy output, unique spectral signatures, and relativistic jets produce distinct and measurable signals that act as cosmic beacons. Understanding these signs is crucial both for early detection and for preparing any response to the potential threat they pose. However, identifying a rogue quasar before it becomes dangerously close remains a complex challenge, demanding detailed analysis across many wavelengths, precise measurements, and ongoing monitoring over extended timescales. The first and most obvious sign that a rogue quasar is approaching is the gradual brightening of an ultraluminous source of electromagnetic radiation in the sky. Quasars shine brilliantly because of their accretion disks, immense swirling masses of superheated gas and dust spiraling inexorably into the central supermassive black hole. As the rogue quasar drifts into regions with fresh supplies of fuel, interstellar gas clouds, star clusters, or galactic outskirts, it begins to reignite or intensify its emissions. This results in a noticeable increase in brightness, sometimes by factors of hundreds or thousands over relatively short cosmic timescales, years to decades in observed terms. This brightening would be most prominent in high-energy wavelengths, ultraviolet, X-rays, and gamma rays, because the accretion process near the black hole releases tremendous energy in these bands. Thus, space-based observatories sensitive to these energies, like the Chandra X-ray Observatory, the XMM Newton, and the Fermi Gamma Ray Space Telescope, would record an unusual and persistent rise in flux from a localized point in the sky. Unlike typical transient sources such as supernovae or gamma ray bursts, which flare briefly and then fade, a rogue quasar's brightness would persist or even grow, lasting decades or centuries, signaling continuous feeding and activity. Spectral analysis provides another crucial sign. Quasars have characteristic emission lines in their spectra caused by highly ionized atoms in the accretion disk and surrounding gas. As a rogue quasar approaches, astronomers would detect broad emission lines of hydrogen, the Balmer series, ionized carbon, oxygen, nitrogen, and magnesium, features that distinguish quasars from ordinary stars or galaxies. These spectral signatures shift depending on the quasar's velocity relative to Earth, a phenomenon known as redshift or blue shift. A rogue quasar moving toward us would produce blue shifted lines, meaning their wavelengths would be shorter than expected, indicating it is coming closer. Detecting and measuring this shift would be a vital indicator of an incoming threat. Another unique sign is the observation of relativistic jets, powerful beams of charged particles accelerated to near the speed of light and ejected perpendicular to the quasar's accretion disk. These jets emit strongly in radio, X-ray, and gamma-ray wavelengths and can extend over millions of light years. Radio telescopes like the Very Large Array, VLA, and the Atacama Large Millimeter/Submillimeter Array, ALMA, can detect these jets' radio emission even if the quasar itself is obscured optically by dust. The appearance or brightening of such jets in unexpected locations, between galaxies or far from known galactic centers, would signal a rogue quasar's presence and movement. Polarization studies provide an additional diagnostic tool. The light from a quasar, especially from its jets, often exhibits strong polarization due to synchrotron emission, radiation produced by charged particles spiraling around magnetic fields. Measuring changes in polarization over time can reveal shifts in the orientation or activity level of the jets, indicating dynamic behavior consistent with a moving and feeding rogue quasar. Timing and variability patterns are further signs to watch. Quasars, including rogues, often display variability in their brightness over timescales from days to years. Monitoring these fluctuations with high-precision photometry allows astronomers to distinguish them from other luminous objects. A rogue quasar entering a new environment may show sudden changes in variability patterns as it encounters fresh fuel sources or interacts gravitationally with nearby matter. Gravitational lensing events may also offer indirect clues. As a rogue quasar passes between Earth and a distant galaxy or quasar, its immense gravitational field can bend and magnify the light of background objects, producing transient brightening or multiple images. Detecting such lensing effects and correlating them with other quasar signatures helps track the rogue's position and trajectory. On the gravitational wave front, although not direct electromagnetic signals, the detection of gravitational waves from recent supermassive black hole mergers can serve as an early warning system. Such mergers are prime mechanisms for ejecting black holes as rogue quasars. If gravitational wave observatories like LISA detect a merger event, astronomers can search the corresponding region for newly active or moving quasars, potential rogue candidates. Importantly, despite these clear signatures, detecting a rogue quasar before it approaches dangerously close is complicated by vast cosmic distances and time delays. Because light takes time to travel, the radiation we observe from a rogue quasar may represent its state millions of years in the past. Thus, by the time we detect brightening or spectral signs, the quasar may have moved closer or farther than indicated. This cosmic latency means that continuous monitoring and modeling of trajectories are essential to predict future behavior accurately. Moreover, rogue quasars may remain quiescent, dark and difficult to detect, when not actively feeding. They can drift silently for millions of years, becoming luminous only upon encountering new gas clouds or star clusters. This intermittent activity pattern complicates early warning, requiring astronomers to maintain vigilant, all-sky surveys and multi-wavelength observations to catch these reawakening events. For planetary systems and civilizations, the approach of a rogue quasar's jets or radiation would initially manifest as a gradual increase in high-energy cosmic rays and X-ray flux. Atmospheric chemistry would begin to change, with ozone depletion and increased ionization detectable in planetary atmospheres. Over time, surface radiation levels would rise, potentially triggering biological stress and extinction events long before the quasar's closest approach. Detecting these precursor environmental changes remotely is a futuristic but conceivable goal for interstellar observation. In summary, the key signs to watch for in identifying an incoming rogue quasar include sustained brightening in ultraviolet, X-ray, and gamma-ray wavelengths, characteristic quasar emission lines with measurable redshift or blue shift indicating motion toward Earth, detection of powerful relativistic jets emitting radio and high-energy radiation, possibly in unusual locations, variability in brightness and polarization consistent with accretion dynamics and jet activity, indirect gravitational lensing events and gravitational wave signals linked to black hole mergers. Despite these identifiable markers, the challenge lies in the timescale and distance scales involved. Rogue quasars are rare, distant, and often dormant, making early detection difficult. Yet advances in multi-messenger astronomy, combining electromagnetic, gravitational, and neutrino observations, promise to enhance our ability to spot these cosmic predators before they approach. By integrating data from multiple observatories worldwide and applying sophisticated machine learning algorithms to parse subtle changes in brightness, spectra, and position, astronomers hope to build a real-time watch system for rogue quasars. Such vigilance is crucial not only for scientific understanding but also for assessing potential cosmic hazards on a galactic scale. Ultimately, while the approach of a rogue quasar would herald a slow-moving but profound cosmic threat, its light signature provides humanity's best early warning system, a faint, distant beacon from the depths of space, signaling a cosmic predator silently making its way through the universe. The good news about rogue quasars is that, despite how destructive and unstoppable they sound, they are phenomenally rare. To understand just how rare, imagine all the galaxies in the observable universe, trillions of them, each with billions or even trillions of stars, and in many cases, a supermassive black hole in the center. Only a small fraction of those supermassive black holes ever become quasars in the first place, and an even smaller fraction of those are ejected from their host galaxies to drift alone in intergalactic space. The cosmic conditions required for a quasar to go rogue are so specific and improbable that, on human timescales, we are talking about events that almost never happen within our neighborhood of the universe. But here's the part that tempers that relief: the universe is big. Not just big in the a lot of miles sense, but so unfathomably enormous that words like infinite start creeping into casual conversation. Even when an event is 1 in a billion, that still means there could be many such events occurring somewhere, simply because there's so much somewhere to begin with. The vastness of space is both our greatest protection and our greatest problem. It's protection because the sheer distances between galaxies and stars mean that most rogue quasars will never come anywhere near us. It's a problem because those same distances make them incredibly difficult to find, track, and study. Light takes time to travel, and quasars, like all cosmic objects, obey that rule. When we observe a quasar billions of light years away, we're seeing it as it was billions of years ago, not as it is today. If a quasar were to go rogue somewhere in a distant galaxy, we might only detect the event long after the black hole has already moved somewhere else entirely. This time delay is one of the main reasons tracking a rogue quasar's movement is so challenging. We're essentially looking at snapshots of the past, trying to predict where a cosmic monster might be in the present, with no ability to fast-forward the footage. And even if we do catch a quasar in action, distinguishing between one anchored in a galaxy and one truly adrift in the cosmic void is not easy. Space is full of faint galaxies that can be difficult to see, and a rogue quasar could appear to be part of a distant, barely detectable galaxy just because of the angle or the way its light interacts with interstellar matter along the line of sight. In some cases, a rogue quasar might not even be producing the kind of dramatic light output that makes quasars famous. If it has exhausted most of the matter around it, it could be quietly coasting through space, invisible except for the subtle gravitational effects it has on nearby stars or gas clouds, effects that are extremely hard to detect unless the object is relatively close by. It's also important to remember that the instruments we use to scan the sky, while incredibly powerful, still have limits. Telescopes like the Hubble Space Telescope, the Very Large Telescope, and the James Webb Space Telescope are marvels of engineering, capable of peering deeper into the universe than any human eyes have ever seen. Yet they can only observe small slices of the sky at a time, and the sky is enormous. Even surveys that scan wide areas, like the Sloan Digital Sky Survey, can only capture so much data, and they're always competing with the simple fact that there are countless other objects, stars, galaxies, nebulae, all pouring light into our instruments. In that overwhelming ocean of data, the light signature of a rogue quasar can be lost, hiding in plain sight until a pattern is noticed years later. On the human timescale, we also have the problem of speed versus scale. A rogue quasar, even if it's drifting at thousands of kilometers per second, takes millions of years to cross significant cosmic distances. That means that if one were heading even vaguely in our direction from several million light-years away, we would have vast amounts of time to notice it, assuming we knew where to look. The unsettling part is that we could easily not know where to look. Its motion might not be directly toward us. It could be sweeping along a trajectory that only intersects our neighborhood of the galaxy after eons of quiet travel. This gives us comfort in knowing there's no immediate danger, but also highlights the reality that such objects, while rare, could be traveling silently through space right now, unseen because we've not yet caught the right photons in our detectors. This is why astronomers often emphasize both the rarity and the uncertainty. The rarity tells us that the odds of one entering our vicinity in the lifespan of humanity are almost negligible. The uncertainty reminds us that the universe is still largely unmapped in 3 dimensions at the precision required to plot every massive object's future course. The truth is that for all our technology and growing understanding, we are still early in the game of cosmic cartography. The other reason we shouldn't lose sleep over rogue quasars is that even when they are detected, they tend to be unimaginably far away. We're talking about distances measured not in light years but in millions or even billions of light years. At such ranges, their jets of energy, while devastating up close, become harmless background noise in our sky. Space is very good at diluting energy. By the time a quasar's light or radiation reaches us from such distances, it has spread so thinly that it's just another pinprick in our night sky, completely harmless to life here on Earth. However, the very thing that makes them harmless from far away, the vast stretches of space, also makes them perfect candidates for remaining undetected until they're much closer. Our galaxy itself is about 100,000 light-years across. A rogue quasar doesn't need to cross intergalactic space to be a threat. If one somehow entered our galaxy's outskirts and lit up again, it could have serious implications for nearby systems. The odds of this happening are minuscule, but because we can't perfectly track every wandering supermassive black hole, it's not something we can definitively rule out for all of time. This is why scientists are so fascinated by the idea of rogue quasars, even if they don't pose an immediate danger. Studying them gives us insight into the most extreme environments in the universe, into the processes that can eject supermassive black holes from their homes, and into the resilience of cosmic structures. But it also keeps us humble. The universe is too vast for us to ever fully monitor, and the forces at play are so immense that our planet is like a speck of dust in a boundless ocean. The good news is that in an ocean that big, the chances of one particular wave ever hitting us are vanishingly small. So yes, rogue quasars are real, and they are powerful beyond anything humanity could survive if one came too close. But they are rare, and space is on our side when it comes to keeping them far away. The trick, and the challenge for astronomers, is that in a cosmos this vast, rare, still means there are likely many of them out there somewhere, silently moving through the darkness, waiting for us to find them. The universe hides its most dangerous secrets well, and while that might sound ominous, it also means that for now, and for the foreseeable future, we can continue to watch the skies without expecting a rogue quasar to appear in our cosmic neighborhood anytime soon. The sheer immensity of space is our shield, even if it also keeps its mysteries just out of reach. Picture it, the universe, silent and endless, a black canvas scattered with faint pinpricks of starlight. Out here, far from the bustling centers of galaxies, there is no warmth, no comfort, no trace of life, only the cold abyss stretching in every direction. And somewhere in this deep, dark ocean drifts a single, solitary beacon. It burns not with the soft glow of a star, but with the raw, unrestrained fury of a cosmic furnace, blindingly bright, unyielding, and alive with energy that could strip the flesh from worlds and boil the atmospheres of planets in seconds. This is the rogue quasar, the homeless predator of the universe, traveling without allegiance to any galaxy, carrying destruction in its wake. Its heart is a supermassive black hole, millions or even billions of times the mass of our Sun, spinning like a titanic whirlpool. Around it swirls an accretion disk of searing gas and dust, spiraling inward at nearly the speed of light. Magnetic fields whip and snap like cosmic whips, and twin jets of charged particles blast outward for millions of light-years, slicing through the dark like searchlights from some unimaginable prison escapee. These jets are more than just light. They're streams of pure radiation, invisible yet deadly, capable of sterilizing anything in their path. But unlike a star that might live in harmony within its galaxy, the rogue quasar is untethered. It has been flung into the void, its home galaxy left far behind, perhaps scarred from the violent gravitational encounter that cast it out. Now it wanders, its hunger unending, its presence a silent threat to anything unlucky enough to cross its path. The most haunting part is the stillness of it all. You might imagine something so powerful would roar through the cosmos, yet the void is silent. No sound travels here, only light and radiation, invisible to human eyes unless you have the right instruments. To a casual observer, there might be nothing to see, until the quasar's light finally reaches you, having traveled for millions of years, carrying the story of its destructive journey across space. For eons, it may pass through empty stretches, drifting without a victim, its light spilling into the darkness like a lighthouse shining on a shore that no ship will ever reach. But the moment it encounters a new source of fuel, a gas cloud, a wayward star, or even the outskirts of a galaxy, it will feed, and in feeding, it will blaze with renewed fury, becoming a danger once more. There's a strange melancholy in its existence. It's not a conqueror with a plan, nor a hunter seeking prey. It is simply what it is, an engine of physics, born of gravity, momentum, and chance. Once, it may have been the luminous heart of a thriving galaxy, surrounded by billions of stars, orbiting serenely in cosmic order. Then, perhaps through a violent collision of galaxies or the gravitational slingshot of another black hole, it was cast out into exile. Now it wanders without purpose except to consume, endlessly devouring whatever falls into its path. Unlike stars that burn out and die, the quasar's light can be reignited again and again, as long as there's something left to eat. Its life is measured not in millions, but potentially billions of years, a lone predator that might outlast even the galaxies themselves. From a great enough distance, it might even look beautiful, its jets stretching like glowing needles across the dark, the halo of its accretion disk shimmering with colors no human eye could see. Astronomers, peering through their telescopes, might marvel at its brightness, unaware, or perhaps too aware, that such beauty hides an almost unimaginable destructive potential. To civilizations that might arise in its path, there would be no negotiation, no preparation, and no survival. The moment they saw its light growing stronger in their skies, it would already be too late. And so it drifts, carrying within it the quiet horror that comes with knowing the universe is not hostile by intent, but by nature. In its indifference lies the danger. There is no malice here, no consciousness deciding to destroy, only the inevitability of physics playing out on a scale too vast for human minds to truly comprehend. Somewhere, in the unimaginable darkness between galaxies, a rogue quasar may be moving at this very moment, a tiny spark in the grand tapestry of the cosmos, yet bright enough to outshine entire galaxies when it feeds. Its light may never reach us, or perhaps it already has, and we simply don't yet recognize it for what it is. It is this image that lingers, a lone light in the dark, a cosmic exile traveling endlessly with no destination, no companions, and no mercy. It has no past to return to and no future to look toward, only the endless present of its journey through the abyss. In the vast theater of the universe, where galaxies swirl like dancers and stars are born and die in spectacular fireworks, the rogue quasar is the quiet, solitary figure moving through the shadows, either part of the performance, nor entirely outside it. It is a reminder that beauty and danger often share the same face, and that in the deep, silent ocean of space, not all lights are friendly beacons guiding you home. Some are predators, shining bright to mark the place where the universe itself is devouring whatever dares to come close. And it will keep drifting, long after our sun has died, long after our galaxy has changed beyond recognition, long after the last human thought has vanished into the void. Somewhere, the lone light will still burn, a wandering monument to the raw, untamed power of the cosmos. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.